Welcome to this comprehensive preparation path for the ServiceNow Certified Implementation Specialist Vulnerability Response exam. This introductory module sets the stage for mastering the certification blueprint and the core mechanics of the platform. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to ServiceNow in any way. All trademarks belong to their respective owners. In this chapter, we will articulate the fundamental architectural, operational, and structural expectations necessary for your success in the CIS-VR exam. We will examine the scope of the certification, the specific domains of the test, and the integration of security operations suites into your existing enterprise ecosystems. Achieving the CIS-VR certification serves as a clear signal of your technical proficiency within the ServiceNow ecosystem. This course is meticulously designed to bridge the gap between abstract theory and the practical constraints of a production implementation. We will navigate through the complexities of data ingestion, risk calculation engines, and automated remediation workflows that define modern security operations. By following this curriculum, you are investing in a structured pathway that ensures you not only understand the platform features, but also grasp the underlying logic required for complex environment troubleshooting. The curriculum is structured around the official exam blueprint, covering everything from initial plugin initialization to advanced orchestration and performance analytics. You will learn to manage the interplay between third-party vulnerability scanners, the National Vulnerability Database, and the ServiceNow Configuration Management Database. We emphasize the critical relationship between asset enrichment and accurate risk scoring, as misconfigured data models often lead to skewed remediation priorities. Furthermore, you will gain insights into the maturity model frameworks, which help practitioners move from reactive patching to a proactive, risk-based vulnerability management lifecycle. To succeed in this field, you must view the platform as a cohesive, integrated architecture rather than a collection of isolated modules. We will deep dive into access control lists, database architecture baselines, and the specific security operations roles required to maintain system integrity. As we progress, you will see how the Vulnerability Response module relies on precise cross-module communication, particularly with change management and incident management within the ITSM suite. Understanding this ecosystem connectivity is paramount, as the exam frequently tests your ability to predict the impact of configurations across these interconnected domains. Platform release compatibility and versioning remain constants in our discussions, as ServiceNow updates introduce nuanced changes to how scanners feed data into our vulnerable items table. You should approach your lab environments with a mindset that favors automation and auditability, ensuring that every grouping pattern and remediation rule you define is built for scale. Expect to encounter deep dives into the logic behind the vulnerability risk calculator, which is often the most misunderstood component by new administrators. We will break down these technical hurdles into manageable, logical chunks that reflect how a seasoned architect approaches a real-world implementation. I look forward to guiding you through this technical journey. See you in the next session. Welcome back to the course. In this lesson, we will begin our exploration of the vulnerability response application architecture by examining the core database schemas and data relationships that form the foundation of the platform. Understanding the underlying database architecture of vulnerability response is not merely an academic exercise, but a prerequisite for building robust security operations. When we look at the core of the system, the Ingestion vulnerable item table stands as the primary entity where security findings reside after being ingested from third-party scanners. This table functions as a refined projection of raw vulnerability data, mapped specifically to the context of your existing configuration items within the CMDB. One must appreciate that this is not a flat storage mechanism. It is a complex relational structure that interacts heavily with standard ITSM models to ensure that security teams can communicate effectively with infrastructure teams. If you ignore the nuances of how these records link to CI records, you will inevitably struggle with operational challenges like noise reduction or asset ownership attribution later in your implementation. At the heart of the operational flow lies the relationship established by the SN_VUEUM2M vulnerability_group table, which acts as the joint entity between vulnerability groups and individual vulnerable items. This many-to-many relationship is critical because it allows a single vulnerability to be managed across multiple organizational contexts or remediation campaigns without duplicating the underlying technical finding. You should view these groupings as dynamic containers that enforce organizational policy rather than static buckets of data. When we configure these structures, we are defining the boundaries of our remediation workflow, effectively deciding how security incidents are bundled for consumption by IT departments. In a high-volume enterprise environment, the overhead of maintaining these relationships can become significant, necessitating a deep understanding of index lookups to prevent performance degradation during large-scale ingestion cycles. Third-party scanner integration relies on specific schema definitions that translate heterogeneous vendor data into a normalized format that the ServiceNow engine can process. This normalization process happens at the ingestion layer, where distinct scanner attributes are mapped into the standardized fields of the vulnerable item model. It is here that scoping rules become vital, as they define which segments of the imported data are relevant to your specific business units and which should be filtered out to maintain system integrity. Think of these boundaries as the first line of defense against data bloat, ensuring that only actionable items are promoted into the operational workflow. When designing these flows, always consider the long-term impact on storage and archiving, as the volume of vulnerability data often grows much faster than standard incident management records. Dependency mapping between security data and the CMDB is perhaps the most complex area of the architecture, as it dictates how we prioritize vulnerabilities based on business impact. Every record in the system ultimately maps to a configuration item, and the integrity of this link determines the accuracy of our risk scoring engines. If your CMDB is lacking, the vulnerability response model will struggle to provide the context necessary for informed decision-making, regardless of how well-tuned your automation flows are. We must treat the data model dependencies, specifically the inheritance patterns from the base task table, as a constrained environment where customization should be kept to a minimum. By adhering to the standard schema definitions provided by the application, we ensure that our implementation remains supportable throughout future platform upgrades and security patches. Structural integrity, especially regarding index optimizations and scoping rules, is what separates a poorly performing instance from an efficient enterprise solution. We must always account for the unique way ServiceNow handles scope tables, ensuring that our access controls do not inadvertently block the underlying system engines that calculate risk scores. Field definitions across the vulnerability landscape are optimized for query performance, which means that adding custom fields without appropriate indexing can quickly lead to slow dashboard rendering and sluggish remediation workflows. As we move through this chapter, keep these underlying structural constraints in mind, as they inform every configuration decision we will make in the coming modules. A disciplined approach to maintaining these boundaries will ensure absolute stability when operating at scale. See you in the next lesson. Welcome back. Let us discuss how to correctly approach the technical activation and structural management of the security plugin ecosystem within ServiceNow. Installing vulnerability response plugins is not merely a matter of clicking an Activate button within the ServiceNow Store interface. It requires an understanding of how scoped applications interact with the platform's underlying schema and existing global baseline configurations. When you deploy the core vulnerability response application, you are introducing a complex set of tables, business rules, and script includes that must coexist with your existing CMDB and ITSM environment. You must verify that your instance satisfies all mandatory dependencies before triggering an installation, such as the required versioning for the Common Service Data Model or specific performance analytics plugins. Skipping these prerequisite checks often leads to corrupted schema deployments that prove notoriously difficult to unwind once the transactional data begins to flow. Once the foundation is set, you will often find yourself layering extension plugins like Application Vulnerability Response or Container Vulnerability Response on top of the base package. These extensions utilize a scoped architecture that limits cross-scope data access, which is a design pattern intended to maintain system stability. When installing these, always monitor the update set tracking to ensure that your local customizations are not accidentally captured or overwritten by the vendor's baseline modifications. Manage your update sets by isolating installation activities from your day-to-day administrative changes. as this separation allows for a cleaner rollback path should an activation fail. It is also good practice to validate the licensing profile associated with the store application to ensure that your current subscription permits the features you are attempting to enable. Troubleshooting activation errors requires a methodical approach, starting with the system log files. Frequently, you will encounter schema validation blocks that occur because of pre-existing records or conflicting configurations in global tables. When you see such errors, examine the system logs specifically for store application error codes, which provide granular details about which specific business rule or dictionary entry caused the transaction to roll back. If you face a situation where a module fails to reach a complete status, resist the urge to perform manual database modifications in the development environment. Instead, focus on validating user criteria and access controls that might be preventing the installation process from writing to protected system tables. Post-installation, your focus must shift toward configuring baseline system properties that govern how the application behaves. Many administrators neglect the SES properties table after installation, failing to realize that these properties control critical functions like automatic grouping and vulnerability calculation intervals. You should systematically review these properties to ensure they align with your organization's risk appetite and technical constraints, particularly regarding how data is ingested from external vulnerability scanners. Furthermore, check the localization controls if your organization operates in a multi-language environment, as label overrides can often be reset during a plugin upgrade or installation. Confirming these properties across all module workspaces provides a definitive assurance that the integration is ready for data ingestion. Finally, consider the structural integrity of your instance in relation to legacy scripts. Over the years, many legacy implementations used hard-coded queries or direct table access that may conflict with the new controlled APIs provided by the Vulnerability Response Suite. As part of your installation process, identify any legacy code that touches the vulnerability tables and refactor those calls to use the provided integration interfaces or scripted REST APIs. This level of diligence ensures that your installation is not just functional on day one, but remains maintainable through future upgrades of the platform. By isolating your structural configurations from temporary workarounds, you build a sustainable security program that can evolve alongside your infrastructure. I will see you in our next session. Welcome back. We are now entering the chapter dedicated to access controls implementation. In this series, we will dissect the fine-grained security model that governs how your organization protects highly sensitive vulnerability intelligence. Securing a ServiceNow Vulnerability Response instance is fundamentally about the principle of least privilege, which implies that a user should only possess the specific permissions necessary to perform their job function. When we look at the core roles, such as s-serval.admin, s-serval.vulnerability analyst, and s-serval.remediation owner, we are defining personas that map directly to the operational workflow of security teams. The administrator holds the keys to the kingdom, including configuration of risk calculators and integration settings, while the analyst focuses on triage and the remediation owner handles the actual patching. Implementing these roles effectively requires a deep understanding of the underlying access control lists that guard the vulnerability task tables. If you fail to configure these ACLs with precision, you risk either exposing sensitive data to unauthorized departments or, conversely, crippling the efficiency of your remediation teams by preventing them from accessing the records they own. The complexity increases when we transition from simple role-based access to explicit data containment profiles, which are often necessary in large, multi-departmental enterprises. You might find yourself in a scenario where a remediation owner in the server team should only view vulnerabilities associated with specific configuration items while remaining blind to endpoint security posture. This necessitates a design where ACLs rely on scripted conditions to evaluate the context of the user against the record being accessed, rather than relying on flat rule checks. Always remember that ServiceNow evaluates these rules from the specific to the general, meaning that a well-placed, narrow constraint will often override broader global definitions. When managing these granular visibility requirements, you must carefully audit role inheritance hierarchies to ensure that a lower-level role does not inadvertently gain elevated privileges through a parent group membership. Contextual read-write restrictions represent the next layer of complexity, particularly when dealing with the life cycle of a vulnerability record as it moves through various states. An analyst might need read access across the entire portfolio, but their write permission should likely be bounded by the state of the vulnerability, preventing modification once a record is closed or marked as pending approval. This logic is best handled via ACL scripts that reference the business object's current status and the user's assignment group. Furthermore, we must address the security of API integration accounts that feed third-party scanner data into your instance. These non-human accounts should operate under a restricted role that lacks interactive session permissions, effectively isolating their capabilities strictly to record insertion and update operations. By enforcing this strict separation, you safeguard against an attacker compromising an integration credential to gain entry into the wider platform user interface. Troubleshooting ACL bypass scenarios is an inevitable task for any administrator who manages a complex vulnerability response deployment. When a user is inexplicably denied access or, conversely, sees too much, the first path of action is to utilize the ServiceNow debug tool for security rules. This tool allows you to observe the evaluation logic in real time as a record is loaded, showing exactly which privilege check failed or succeeded. Often, a perceived bug is actually a collision between multiple overlapping ACLs, or a failure in the evaluation of a script include used in a condition. Maintaining separation of duties is critical in production environments, as an improper configuration could allow a remediation owner to both trigger a vulnerability exception and approve it. By systematically auditing these rules, you maintain the integrity of your security posture while ensuring that audit trails remain clean and compliant with internal policies. Finally, secure delegated assignment scripts provide the mechanism to automate the distribution of work without manual, high-privilege intervention. These scripts function as a guardrail, ensuring that when an automated rule assigns a vulnerability task to a group or user, that target entity actually possesses the rights to edit that specific record. Implementing this correctly prevents the creation of orphan tasks that exist in a permission void where no one can take action on them. By centralizing this logic in a dedicated script you make your security architecture more maintainable and easier to test during your pre-production validation phases. Always document these custom conditions clearly within the system, as the complexity of multi-layered ACLs can grow significantly over time and become difficult for future administrators to troubleshoot. This systematic approach to access control is what defines a mature, robust vulnerability management program. See you in the next session. Welcome back. In this lecture, we begin our exploration of vulnerability response maturity model frameworks to understand how organizations evolve from manual processes to automated risk-aware operations. When we approach the vulnerability response maturity model, we are essentially looking at a spectrum that dictates how data flows from discovery to remediation. At the lowest level of maturity, organizations often operate in a reactive state, relying on manual data entry and spreadsheet-based tracking to manage patches. This level is characterized by a lack of integration between discovery tools and the platform, leading to significant delays in identifying critical exposures. As we move up the tiers, the focus shifts towards centralizing vulnerability data through authorized feeds and scanners, which starts to break down silos. The primary goal during this phase is to ensure that every vulnerability is accounted for within the Configuration Management Database, or CMDB, linking security data to tangible infrastructure. Without this foundational mapping, any attempt at automation will inevitably collapse under the weight of unstructured and untrusted data points. As an organization matures, it must transition from simple vulnerability identification to a more nuanced process of risk-based prioritization. In the higher tiers of the model, you no longer treat every vulnerability as a critical incident by default, but instead apply logic based on the actual business context of the asset. This requires a deep understanding of impact assessment workflows and how to leverage the scoring engine to calculate risk dynamically. When you move toward enterprise risk trending, you are essentially building a feedback loop where metric definitions inform future policy changes and resource allocation. Operational guardrails begin to play a vital role here, ensuring that owner assignment models remain consistent even as the volume of vulnerable items scales across the enterprise. You are essentially building a machine that evaluates its own health. using performance analytics to report on remediation velocity and exposure gaps automatically. The transition criteria between these maturity levels should never be arbitrary, as they must be rooted in the operational readiness of your team and the quality of your asset metadata. You need to analyze whether the organization has the capacity to handle automated assignments before you configure them, or you risk flooding your technical teams with noise. Effective implementation involves planning progressive rollout phases where specific processes, such as exception management or group assignment, are hardened before they are scaled out. By mapping real-world organizational parameters against these standard maturity levels, you can identify specific process gaps that prevent efficient remediation. For instance, if your reconciliation logs consistently show failed matching between discovery data and the CMDB, you have a clear metric indicating that you are not ready for a higher tier of automated grouping. Scaling processes efficiently requires this methodical approach, where each configuration is verified against the intended business outcome, rather than just the technical capability. Building a scalable and secure structural roadmap requires acknowledging that maturity is not a static endpoint, but a continuous improvement cycle. You must consistently audit your prioritization rule logic to ensure it aligns with the evolving threat landscape and the changing criticality of your assets. As you advance, you should replace hard-coded assignment rules with dynamic flows managed by the platform, ensuring that ownership transitions are seamless when infrastructure changes. The ultimate objective is to reach a stage where your reporting dashboards provide actionable intelligence to stakeholders, enabling them to make informed decisions without diving into raw data. When you achieve this, the system acts as a force multiplier, reducing the mean time to remediate and allowing your security team to focus on strategic risk mitigation. This transformation is only possible if you treat the model as a framework for standardizing operations, not merely as a feature checklist to satisfy audit requirements. See you in the next lecture. Welcome back. This lesson focuses on the Setup Assistant, our primary tool for bootstrapping the vulnerability response environment. We will examine how this wizard-driven interface orchestrates the baseline technical configuration of the application. The Setup Assistant serves as an automated orchestration layer designed to reduce manual configuration errors during initial deployment. By navigating through its guided paths, you initialize the fundamental parameters required for the Vulnerability Response module to function within your instance. This tool is not merely a documentation guide. It is an active configuration engine that writes values directly to property tables and alignment records. When you step through the workflow, the assistant prompts for global settings such as default assignment groups and baseline risk calculation models. These decisions dictate how vulnerable items are ingested, prioritized, and eventually routed to the correct remediation teams. It is essentially about establishing a consistent system architecture that remains maintainable as your vulnerability management program matures and scales across the enterprise. Behind the user-friendly interface, several hidden configuration tables and property definitions are updated in real time. If you find that the assistant is blocked, it often relates to missing system prerequisites or existing conflicts in the configuration item classification layers. To troubleshoot these blocks, you must look at the specific property names referenced by the assistant during execution and verify their values in the System Properties table. Some organizations mistakenly believe that the setup wizard is a one-time operation, but it is often useful to return to these snapshots to review structural alignment. By managing the installation validation checks, you ensure that your deployment stays within the boundaries of established compliance standards. If the assistant flags a warning, it is almost always pointing toward a discrepancy in how your asset profiles or risk calculators are initialized. During the configuration process, you define baseline risk calculators that determine the initial score of a detected vulnerability. This is a critical architectural decision because these calculations ripple through your entire remediation lifecycle. You must ensure that the assignment paths are mapped to active, functional groups within your instance to prevent orphans from staying in a new state indefinitely. The Setup Assistant also facilitates the alignment of standard system schedules, which govern how frequently background jobs pull data from external scanners or update the centralized vulnerability database. When we orchestrate these structural asset profiles, we are effectively setting the rules for how the system recognizes and categorizes hardware and software. A well-configured setup assistant run acts as the foundation for clean metrics and accurate reporting throughout your time using the platform. See you in the next lecture. Welcome back. In this session, we turn our focus to the architectural configuration and personalization of your operational consoles, specifically the IT remediation and vulnerability manager workspaces. When we discuss workspace environment personalization, we are not simply talking about aesthetic choices or changing colors. We are looking at the foundational UX component structures that dictate how a remediation analyst interacts with high-volume technical data. The goal is to maximize the utility of the Vulnerability Manager workspace by manipulating the landing page configurations to surface actionable intelligence immediately upon login. By leveraging the underlying Now Experience framework, we can refine the card designs to prioritize critical vulnerabilities while shielding teams from excessive noise. This requires a disciplined approach to filtering frameworks and list component adjustments, ensuring that the interface remains a tactical tool rather than a static document. Every modification effectively acts as a mediator between raw security data and the human decision-making process. To deliver this efficiency, we must categorize our data views based on distinct user personas. A remediation engineer requires a view filtered by assignment groups and imminent SLA breaches, whereas a security manager benefits more from aggregate risk trends and volumetric analysis. You achieve this by configuring unique workspace variants that cater to these specific operational requirements. When you modify list components, you are essentially defining the subset of back-end table data that flows into the interface. We must be careful to optimize these queries to avoid latency, as poorly structured filters will directly impact the responsiveness of the workspace. Creating these targeted views ensures that the interface remains lightweight while providing the depth necessary for complex remediation tasks. Wiring the workspace analytics engines introduces a layer of dynamic visual telemetry that requires precise configuration. We integrate these engines to provide real-time visibility into the lifecycle of vulnerable items, which informs the prioritization logic used by the field teams. When we discuss ribbon configuration issues, we are often addressing the alignment between the ribbon headers and the underlying record context. If the ribbon fails to reflect the current state of a vulnerability group, the analyst loses the mental model of the remediation status. This setup requires careful attention to integration blocks that connect the front-end components to the back-end tables. Furthermore, we must account for potential layout persistence bugs that can occur during upgrade cycles or when custom overrides are applied to the default configuration. Debugging these interfaces is an exercise in trace-oriented development. When you encounter client script errors within the workspace, you should utilize the browser console to identify whether the issue originates in the component lifecycle or the backend response. We lean heavily on the standard debugger patterns to inspect the data stream when a card fails to render or a filter list returns empty results. Security analysts often rely on the consistency of the workspace to maintain their velocity, so any deviation or technical debt in the interface logic needs to be addressed with high priority. By treating the workspace layout as a set of managed configurations rather than a static template, you ensure that your security console remains robust and scalable. Always keep the underlying data models and the UX component lifecycle in sync to prevent the fragile state that often plagues poorly maintained dashboard environments. I will see you in our next technical deep dive. Welcome back, and today we turn our attention to the essential technical groundwork required for integrating third-party vulnerability scanners like Qualys, Tenable, or Rapid7 into our ServiceNow environment. When we begin the process of integrating a third-party scanner, the foundation of our work rests on the connection profile. In the ServiceNow platform, this isn't merely a set of credentials. It is a structured record that defines how the application interacts with external services. We must first verify the existence of the appropriate MID server, as this acts as our secure gateway across network boundaries, effectively shielding our internal infrastructure from direct public-facing exposure. Once the MID server is verified as up and running, we move toward configuring the specific API connection endpoints provided by the vendor. This requires us to input correct base URLs, ensuring that the integration knows exactly where to push queries or retrieve vulnerability assessment data. Any deviation in the API structure here will lead to immediate communication failures, which can be notoriously difficult to debug if we do not approach the initial setup with strict attention to protocol documentation. Authentication within these integrations typically centers on either OAuth, API keys, or standard basic authentication patterns, each requiring careful placement within the ServiceNow credential store. Never store raw credentials directly in the integration script include or the connection profile record itself, as this would violate basic security hygiene and audit requirements. Instead, we use the ServiceNow credential management system to store, obfuscate, and periodically rotate these authentication artifacts, shielding them from accidental exposure in logs. During this stage, we also define the operational window through job schedules. By setting these schedules, we dictate when the integration should trigger a fetch request, helping to distribute the load on both the ServiceNow instance and the scanner's own backend infrastructure. If we schedule too many concurrent requests, we risk bottlenecking our own instance, or conversely, triggering rate limits on the vendor side. Performance tuning is perhaps the most critical yet overlooked aspect of the third-party scanner integration lifecycle. We often find that default configurations do not account for the sheer scale of modern vulnerability datasets, requiring us to adjust multi-thread request streams. By modifying the performance profile, we can increase the throughput of incoming data, though we must do so cautiously to avoid target system fatigue. It is often wise to start with conservative thread counts and increment them only after observing the stability of the ingestion process. During these early runs, you should actively monitor for timeout exceptions in the system logs to identify where network latency or API congestion might be interrupting the data flow. A successful integration is not just one that authenticates, but one that maintains a predictable cadence of data delivery without overwhelming the underlying resources of our platform. Finally, we must consider the rigorous testing required to ensure these integrations remain robust under stress. Developers often rely on unit tests for code, but here we require connectivity validation by manually testing REST or SOAP endpoints using the ServiceNow REST message or SOAP message functionality. By triggering a test message, we can inspect the raw HTTP response codes, payload delivery structures, and header information before formalizing the scheduled jobs. If a payload returns a non-200 status code, we analyze the response body to determine if the issue stems from a faulty authentication, a misconfigured mid-server, or an invalid request parameter. This systematic approach, building the profile, securing the credentials, tuning the throughput, and verifying the endpoint reach, ensures that our vulnerability response module remains well fed with accurate, timely data from our scanners. I look forward to discussing the next phase of our integration journey with you shortly. Welcome back. Let's explore the technical nuances of how vulnerability response handles large-scale data ingestion from external scanners. When we discuss the ingestion of vulnerability data into the ServiceNow platform, we are primarily looking at the mechanics of the import set mechanism. The process begins when an external scanner, such as Qualys, Tenable, or Rapid7, pushes a payload, which often arrives as a structured JSON or XML file. These payloads land in the import set tables, which act as a staging area to ensure that we do not write directly to the production tables without first verifying the structural integrity of the incoming data. Because these files can contain hundreds of thousands of vulnerability findings, the platform utilizes import set transformers to translate staging data into the normalized vulnerability item records. If the incoming payload is malformed or contains unexpected fields, the transformer must be robust enough to log the error without causing the entire processing job to crash. We often see practitioners struggle with record deduplication at this stage, so it is vital to understand that the identifier used during the transform map is critical to preventing the creation of duplicate records for the same vulnerability on the same configuration item. Achieving high performance during these ingestion cycles requires an architecture that favors asynchronous processing rather than synchronous blocking operations. When dealing with high-volume feeds, we must consider the use of chunking configurations, which allow the system to break down massive payloads into smaller, manageable units of work before they hit the transformation scripts. If you are noticing transactional performance metrics degrading, it is likely due to synchronous script execution that locks specific records while the transform map attempts to perform complex lookups. To eliminate these record locking conditions, One should aim to offload heavy calculations to background jobs and ensure that the transformation scripts are optimized for speed. This often involves replacing standard database queries within the scripts with more performant glide record variants or utilizing indexed lookups that point directly to the configuration management database headers. By establishing a stable processing baseline, we ensure that the continuous flow of data does not overwhelm the instance resources during peak assessment windows. Error handling and data formatting discrepancies are inevitable when integrating third-party systems, so building a proactive strategy is a hallmark of a sound implementation. When a scan file arrives with data types that do not align with our predefined target fields, the transform map usually fails unless we have implemented explicit scripts to handle data type coercion. Developers should spend time analyzing the transformation logs to identify systemic patterns in data misalignment, as these errors provide the most reliable feedback loop for tuning the integration. Furthermore, the concurrency configuration settings within the import set architecture allow you to define how many threads can process transformations simultaneously. While increasing the thread count can improve throughput, it also increases the risk of contention on shared tables, so one must balance volume against system stability. Always monitor the import set row processing speeds after adjusting these threads, as a poorly tuned concurrent system often achieves diminishing returns due to overhead contention. See you in the next lecture. Welcome back. In this session, we will examine the integration mechanics of the National Vulnerability Database within your ServiceNow Vulnerability Response instance. The National Vulnerability Database, or NVD, serves as the primary repository of vulnerability management data, and your capability to ingest this information efficiently is foundational to a mature security posture. When we talk about this integration, we are effectively discussing the translation of external structured JSON data streams into actionable local records that your security teams can actually use. You should think of this as a pipeline architecture where ServiceNow acts as a subscriber to the NIST-provided feeds. The configuration requires careful attention to the scheduled jobs that trigger these downloads, as a failure to manage the cadence of these updates leaves your vulnerability response engine operating on stale or otherwise incomplete threat intelligence. You must ensure that your instance is configured to handle the volume of data coming through these feeds, particularly when initializing a new environment that requires an initial bulk sync of the entire historical repository. Managing the ingestion process involves more than just enabling a scheduled job. It often requires a nuanced understanding of proxy settings and authentication layers if your corporate network architecture mandates traffic routing through a gateway. ServiceNow uses specific integration instances to perform these tasks, and you must verify that the endpoint connectivity is consistently maintained. When the raw payload arrives, the platform relies on parsing engines to map elements like Common Vulnerability Scoring System, or CVSS scores, and Common Weakness Enumeration, or CWE, associations into the vulnerability entry records. If you observe discrepancies in your reporting, the issue frequently resides within the parsing logic that interprets the incoming JSON structure. A persistent challenge within this domain is the variance in how product information is represented, necessitating precise synchronization with the Common Platform Enumeration, or CPE, dictionary. Troubleshooting these integrations is a distinct skill set that separates those who maintain a healthy system from those constantly battling sync errors. When you encounter a failure in a daily Delta update, start by auditing the SSSS integration log table to identify exactly where the payload formatting shift or database timeout occurred during the transaction. Large initial syncs are particularly prone to timing out if the underlying processing engine is resource constrained, so architectural strategies, such as breaking the import into smaller asynchronous batches, often provide a more robust path to consistency. Furthermore, you should construct recovery scripts that can resume sync operations from the last successful checkpoint, rather than forcing a full reset, which is both time-consuming and unnecessary. Keeping an eye on the health of your CPE associations ensures that when a new vulnerability arrives, it is correctly mapped to the software products already present in your asset inventory, preventing a drift between threat intelligence and local coverage. See you in our next technical discussion. Hello again. Let us discuss how we bridge the gap between traditional infrastructure and the ephemeral nature of cloud-native environments. In this lecture, we are diving deep into cloud container integration, where we will learn to master the complexities of mapping modern cloud and container security data into the ServiceNow ecosystem. By the end of this session, you will understand exactly how to ingest vulnerabilities from tools like Wiz or Tenable Cloud Security and ensure they reside properly within your configuration management database. Modern cloud environments present a unique challenge because assets are no longer static items sitting in a rack. Instead, we deal with containers and serverless functions that may exist for only minutes, yet carry significant security risks that demand our attention. Integrating these technologies requires us to move away from traditional host-based thinking and embrace a schema that respects the volatility of the cloud. When we deploy integrations for cloud platforms, we are effectively designing a pipeline that translates transient metadata into persistent security records. This process hinges on our ability to map specific cloud resources to the correct infrastructure layers so that the vulnerability response engine can accurately calculate risk. We must carefully configure identification parameters to ensure that every container image or serverless function is tracked even after it has been decommissioned from the production environment. To handle this effectively, we must focus on the data parsing logic that occurs during the ingestion of external vulnerability feeds. When a tool detects a flaw in a container image, it provides a descriptor, but that descriptor might not inherently match a configuration item in our CMDB. We solve this by establishing robust mapping rules that leverage specialized schemas, ensuring that image repository profiles are normalized before they hit the vulnerability assessment workspace. If our integration fails during this data transformation phase, we lose the ability to correlate cluster runtime vulnerabilities with their source. Furthermore, by managing the serverless security records through these automated pipelines, we ensure that the vulnerability status follows the code, not just the underlying resource. This requires a shift in how we think about asset tags, making them dynamic attributes that are ingested alongside the vulnerability data rather than being added as an afterthought by a manual process. When we encounter API mapping failures, it is usually because our identification rules are too rigid for the fast-paced nature of cloud resources. We need to implement reconciliation strategies that can identify non-traditional host records based on unique identifiers like container image digests or specific cloud provider resource IDs. Once the metadata is normalized, we then establish unified remediation structures that allow our teams to patch vulnerabilities at the infrastructure layer or the image level. This systematic approach ensures that every vulnerability identified by a cloud tool has a corresponding, actionable record in ServiceNow, enabling a seamless transition from discovery to remediation. By maintaining this architectural integrity, we avoid the clutter of ghost assets while keeping our security posture completely transparent to the rest of the organization. Focusing on these ingestion parameters will fundamentally change how your team addresses risks in containerized environments. I look forward to discussing the next section with you. Hello, welcome back. In this lesson, we will explore the mechanisms for syncing external vendor security advisories into your environment to proactively identify potential risks. Vendor advisory synchronization is a critical process for modern security operations because it moves us beyond simple vulnerability scanning. While scanners tell you what is currently present on your network, vendor advisories often provide early warnings about vulnerabilities identified by software manufacturers before they are widely exploited in the wild. This capability relies heavily on the Common Security Advisory Framework, which provides a standardized JSON-based format for exchanging security information. When we talk about these integrations, we are essentially building a bridge between external data sources and our internal software inventory. The goal is to move from reactive patching to a capability where we can anticipate a threat based on the vendor's own disclosures. If you think about the software supply chain, these advisories act as our primary signal for software that might not be detected by a credentialed scan, but definitely poses a liability. To implement this effectively, we must first look at the data feed configurations that bring these JSON payloads into the ServiceNow environment. These feeds are typically governed by scheduled jobs that ingest data from vendor portals or specialized security aggregators. The platform uses specific parsing logic to decompose these complex structures into actionable records within the vulnerability response module. Often, developers find that the raw data is quite voluminous, so we must be precise about what we ingest. You have to configure the mapping between the vendor's provided product information and your own internal asset classes, likely within the configuration management database. Without a strong linkage between the vendor's nomenclature and your internal naming conventions, such as your product name or CPE strings, the data becomes noisy and largely unactionable. Once the data is ingested, the next step involves automated patching, metadata extraction, and product impact cross-referencing. The platform reads the vulnerability details, such as the CVE identifier, the severity score, and the specific version range impacted by the advisory. You are essentially creating a matrix where the vendor advisory is compared against your existing software installation list to surface potential matches. This requires a robust set of match parameters, often involving regex or precise component matching, to ensure you are not flagging hardware or software that is not actually present in your stack. If your matching logic is too broad, you will encounter high volumes of false positives, which is an anti-pattern that quickly destroys the trust of your stakeholder groups. You should prioritize defining criteria that narrow down to specific software editions and build numbers whenever possible. Troubleshooting processing errors is a reality you must prepare for, particularly when handling complex CSAF JSON payloads that might deviate slightly from expected schemas. When a feed fails to update or a record fails to create, the first place to investigate is the integration log and the specific transform maps that handle the payload parsing. If match keys are broken, it usually points to a mismatch between how the vendor formats their product identifiers and how you have cataloged those items in your CMDB. You might find it necessary to implement custom scripts that normalize these strings before the matching engine attempts its lookup. Furthermore, as your inventory grows, queries that cross-reference advisories against thousands of configuration items may experience latency issues. You can optimize these lookups by indexing key fields or structuring the data ingestion to narrow the scope of the reconciliation before the process hits the main database tables. Finally, we need to structure automated advisory tracking alerts so that the right people get informed without being overwhelmed. The platform allows you to create alerts based on specific criteria, such as when a critical advisory is matched against your internet-facing assets. These alerts should be actionable, meaning they should contain links to the relevant assets and the suggested mitigation path provided by the vendor. By mapping these remediation steps early, you provide your IT operations teams with clear instructions, which is far better than simply throwing a raw CVE identifier their way. This systematic approach, from ingestion to matching and eventually to alerting, is what separates a mature vulnerability response program from a basic setup. It requires continual tuning of your match keys and careful oversight of the integration health, but the effort pays off in the form of significantly improved security posture. I hope this helps you understand the integration architecture. See you in the next lesson. Welcome back. In this lesson, we will focus on the diagnostic strategies required to isolate failures within your vulnerability integration ecosystem. Troubleshooting integration architecture is less about luck and more about maintaining a disciplined trail of evidence across the ServiceNow platform and the connected scanners. When an integration fails, the first point of failure is often the communication channel between the mid-server and the underlying vulnerability scanner. You should always start by examining the ECC queue, specifically looking for payloads that are marked with an error state or that have failed to transition to a process status. These payloads contain the raw XML response from your scanner and are the single most important diagnostic tool for identifying authentication issues, request timeouts, or malformed data packets that prevent ingestion. If the ECC queue displays a standard processing cycle, you must pivot your attention to the integration logs within the System Import Sets module. By reviewing the import sets, you can determine if the data arrived at the instance but failed due to schema mismatches or field mapping errors that prevent the record from being committed to the target table. Data mapping bugs represent a significant class of issues, often arising when scanner vendors update their API response formats without prior notification. To resolve these, you need to examine the script includes that handle the transformation logic between the raw staging tables and the final vulnerable item records. By adding localized logging statements, using gs.info or gs.debug, within these transformation scripts, you can inspect the data payload at various stages of the transformation pipeline to see exactly where a field maps incorrectly or where a null value disrupts the business logic. This is also the right time to analyze the transaction profiles for the user account associated with the integration. If you are seeing persistent 403 forbidden or 401 unauthorized. Welcome back. In this lecture, we examine the mechanics of configuration item matching within the Vulnerability Response module, focusing on how incoming vulnerability data correctly maps to existing assets in your CMDB. When vulnerability data arrives from third-party scanners, the system must decide whether an entry corresponds to a known asset or represents an unknown entity. This process relies heavily on the Identification and Reconciliation Engine, or IRE, which acts as the architectural gatekeeper for CI data. At its core, matching is governed by lookup rules that compare attributes provided by the scanner against attributes stored on existing CIs. If you look at standard implementations, you will notice that this is not a single pass check, but a structured evaluation hierarchy. The engine first attempts to find a match using high-confidence identifiers, such as a serial number or a unique system UUID, before falling back to less specific markers like IP addresses or host names. Understanding the sequence of these lookup parameters is essential because the order of operations dictates the accuracy of your CMDB health. If your matching criteria are too broad, you risk creating duplicate records or associating vulnerabilities with the wrong assets, which ultimately compromises your risk posture. Precise rule weights allow you to prioritize certain attributes over others during the reconciliation process, ensuring that the most reliable data sources retain authority. Field normalization serves as a critical prerequisite for effective matching, as raw data from disparate scanners rarely arrives in a consistent format. Before the engine even attempts a lookup, the system can parse and transform attributes to ensure a common baseline for comparison. For example, if one scanner reports a host name in lowercase and another in mixed case, normalization rules ensure both represent the same unique asset. You must configure these normalization behaviors within the vulnerability response setup to avoid frequent matching misses that later require manual intervention. Furthermore, the ability to audit lookup paths is highly valuable when investigations become necessary. By reviewing the reconciliation logs, you can determine exactly which matching rule triggered a link or why an asset remained unallocated. This level of transparency into the matching sequence allows you to fine-tune your criteria algorithms iteratively. When you observe a pattern of incorrect asset association, the issue often stems from overlapping criteria where two rules compete for the same attribute, leading to ambiguous results. Effective asset linking requires a proactive approach to reconciliation, especially when dealing with complex enterprise environments where assets are frequently decommissioned or repurposed. You should establish explicit reconciliation priorities that honor the historical integrity of your records, ensuring that vulnerability information stays attached to the correct lifecycle stage of a CI. If your lookup sequence consistently misses, consider the density of your attributes and whether they provide enough distinction to uniquely identify a record. Often, the root cause of a misidentified asset link is a lack of data cleanliness in the source system, which cascades down into your CMDB. By building robust multi-attribute lookup patterns, you create a fail-safe mechanism that maintains data accuracy even when primary identifiers are missing or incomplete. Remember that the engine is highly configurable, but it requires diligent maintenance to balance performance with correctness. Your goal is to maximize the automated linking process while minimizing the noise generated by false positives or unlinked vulnerability items. I look forward to discussing the next topic with you. Welcome back. Let's begin our exploration of handling unallocated IT assets within the vulnerability response ecosystem. In this session, we investigate the mechanisms for managing discovery gaps where IT infrastructure items fail to find a direct match in the configuration management database. When a scanner identifies a device or application, it provides a payload of discovery data that the platform must interpret. Ideally, a matching rule identifies the corresponding configuration item, but reality often presents us with discovery gaps where this automated mapping fails. These are categorized as unallocated IT assets, which represent potential blind spots in your vulnerability posture. If an asset is visible to your scanners but not effectively modeled within your CMDB, you cannot accurately assess its risk or track associated vulnerabilities. We must therefore establish robust bucket strategies to capture such unknowns. By defining specific classification rules for partial network profiles, we ensure that these items do not simply vanish into a void, but are preserved for investigation. This process requires a disciplined approach to tracking, where every unmatched item is assigned to a staging area for further review. Maintaining a clean database is not merely about storage, it is about visibility and maintaining the integrity of our security operations. Building automated bucket strategies allows your team to handle unidentified infrastructure without manual intervention for every single anomaly. We start by configuring classification rules that examine the metadata provided by scanners, such as IP address ranges, MAC addresses, or partial host names. When a discovery process encounters an item it cannot reconcile, the system places it into an unmatched buffer. You should design manual reconciliation flows that empower your asset managers to review these items periodically, deciding whether to promote them to the CMDB or discard them as noise. Consider the case where a network segment is scanned for the first time. The volume of unmatched assets might be overwhelming. By implementing bulk data enrichment tasks, you can automate the process of adding descriptive tags or categories to these items, which helps in grouping them for easier batch reconciliation. This strategy transforms a flood of raw, unlinked telemetry into a structured set of actionable records. Technical debt often manifests as historical heaps of unassigned items that clutter your buffers and impair system performance. We must address rule loop exceptions that occur when classification rules fire repeatedly without resolving the identity of the asset, potentially consuming cycles that should be allocated elsewhere. To manage these, it is effective to construct automated notifications that alert your network discovery teams whenever the volume of unallocated assets exceeds a defined threshold. This keeps the people responsible for discovery in the loop, providing them with the data necessary to improve their scanning configuration or CMDB population logic. If you leave these buffers to grow indefinitely, you will eventually face degradation in detection speed and accuracy. Regular maintenance, including the clearing of stuck buffers and the pruning of stale records, is an essential facet of a mature vulnerability response program. Always aim for a steady state where the gap between discovered reality and the CMDB model is managed with defined, repeatable processes rather than ad hoc cleanup. I will see you in our next discussion. Hello again. Let us explore the mechanics of software exposure analysis within the ServiceNow Vulnerability Response framework. This process is essential for bridging the gap between discovered software inventory and actionable vulnerability intelligence. When we talk about software exposure analysis, we are fundamentally discussing the process of cross-referencing discovered software installations against vulnerability definition indices, such as the National Vulnerability Database. This mapping operation relies heavily on the integration between the software asset management product and the vulnerability response module. You essentially take the existing software model data found in the configuration management database and correlate it with ingested Common Platform Enumeration or CPE records. If the installation records do not contain a standardized CPE string, the system must employ pattern matching or regex-based heuristics to identify relevant vulnerabilities. This is why the quality of your discovery data is paramount, as a missing publisher string or an ambiguous version sequence will directly impact the accuracy of your exposure assessment. The architecture of this integration frequently involves scanning for specific file path dependencies or executable signatures that signify a vulnerable component version. Rather than relying on simple asset names, the engine performs granular package mapping to determine if a specific library or module is actually present on a target configuration item. When you configure the automated exposure calculation engine, you define the logic by which these version strings are interpreted against known risk vectors. It is helpful to view this as a translation layer where proprietary software vendor naming conventions are mapped to industry-standard vulnerability identifiers. However, this level of abstraction often leads to version pattern false positives if the software discovery scanner interprets a minor patch or build number differently than the published vulnerability advisory. Managing these large-scale, multi-platform vulnerability matrices requires you to handle micro-component risks with a high degree of precision. You often encounter situations where a single software suite contains dozens of individual components, each with its own lifecycle and security profile. If your configuration is not tuned, the system might trigger vulnerability items for components that are present on the disk, but not actively executing or exposed to network threats. To mitigate this, you must refine your tracking by focusing on the executable paths and service states recorded during the discovery phase. This ensures that the exposure assessment remains grounded in the actual technical reality of the asset rather than just an inventory count of files. Optimization of the underlying assessment scripts is a recurring theme when dealing with enterprise-scale environments. Because the calculation engine potentially loops through millions of software installation records, poorly constructed queries or excessive regex operations will degrade system performance. You should aim to optimize these lookups by ensuring the relevant CMDB tables are properly indexed and that the reconciliation routines are scheduled for off-peak hours. When you identify performance bottlenecks in the exposure assessment flow, start by investigating the reconciliation logs. These logs provide a window into the normalization process and often highlight where the system struggles to bridge the mapping gap between a raw discovery record and a structured vulnerability definition. Finally, managing the lifecycle of these exposure records implies a robust approach to handling missing metadata. It is common for legacy or specialized applications to lack the detailed publisher information necessary for automated linking. In these cases, you are responsible for defining manual overrides or custom discovery profiles that help the system categorize the software correctly. By consistently refining the software model and its association with the CMDB, you create a sustainable pipeline of vulnerability data. This rigor ensures that when an emergency patch requirement arises, your exposure analysis is already accurate, up to date, and ready to drive your remediation workflows without ambiguity. I will see you in the next lecture. Welcome back. In this session, we will explore the mechanisms of asset group tagging and how it bridges the gap between raw infrastructure data and actionable business context. Asset tagging is not merely a metadata exercise. It is a fundamental requirement for effective vulnerability prioritization within the ServiceNow ecosystem. When we talk about programmatic asset tagging, we are referring to the systematic enrichment of configuration items, or CIIs, with business context that standard discovery tools often miss. By defining precise dynamic asset queries, we can move away from manual record updates and rely on the engine to maintain our inventory groupings based on real-time CMDB states. Think of this as a declarative mapping where the data itself dictates its security significance based on its attributes. We achieve this by configuring tag definitions that evaluate CMDB group structures, effectively creating virtual containers for your assets that span across multiple classes and network topologies. The complexity usually arises when dealing with inheritance logic across related tables. These dependencies require a robust approach to how group membership is calculated and assigned to prevent system bloating or logic errors. When you configure automated business unit tagging scripts, you must ensure they operate based on defined trigger conditions rather than running indiscriminately. These scripts look for specific data points, perhaps a combination of a location attribute and a service instance, to assign a tag that carries weight in our vulnerability impact calculations. By linking these assets to security ownership profiles, we establish a clear path for accountability, ensuring that when a vulnerability is ingested, it is automatically routed to the correct stakeholder. The inheritance logic ensures that these tags flow down from parent services to child components, maintaining consistency across the infrastructure hierarchy. Performance is a frequent concern when dealing with large-scale environments where thousands of dynamic groups are constantly being reevaluated. If you observe lag in your dynamic group evaluation jobs, the culprit is often either overly broad query conditions or excessive recursive lookups that degrade transaction performance. To debug these scenarios, we must inspect the processing logs to identify which rules or queries are consuming the most compute cycles, often requiring a refinement of the underlying CI filter conditions. Furthermore, broken tag inheritance trees usually point towards schema changes or mid-process updates where the parent relationship integrity has been compromised. In these instances, a structured audit of the tag definition helps isolate the conflicting rule that is preventing the expected metadata propagation from completing. Configuring critical infrastructure flags represents a specific pattern where we leverage network topology to infer security risk. By integrating information about whether a server resides within a critical subnet or acts as a gateway, We can programmatically set security flags that inflate the vulnerability score. This approach treats your network layout as a source of truth for risk assessment, allowing for a much more nuanced response than a generic severity score would provide. Management of lifecycle metadata is equally important, as it prevents dead or decommissioned assets from skewing your vulnerability metrics. By programmatically sunsetting tags on assets that have left production, we ensure that remediation teams aren't chasing ghosts in the infrastructure. Effective tagging relies heavily on the ability to resolve rule conflicts when multiple criteria attempt to assign competing tags to the same asset. ServiceNow handles these conflicts through defined precedence orders, and failing to account for this can lead to unpredictable classification of your vulnerabilities. We address this by establishing a clear hierarchy in our tagging definitions, ensuring that non-negotiable security tags always take precedence over operational department tags. When we synthesize these elements together, we create a reflexive system that understands the business value of every digital asset it scans. This level of automation is what separates a mature vulnerability response practice from one that spends the majority of its time adjusting manual assignment rules. See you in the next lecture. Welcome back. We are now entering the specific domain of data deduplication, where we focus on refining how incoming findings are processed and stored within your environment to ensure architectural integrity. When we talk about data deduplication in the context of vulnerability response, we are essentially discussing the mechanisms used to ensure that a single vulnerability on a specific asset does not result in the creation of multiple redundant vulnerable item records. If you imagine an environment where multiple scanning tools are reporting on the same infrastructure, you quickly arrive at a scenario of data noise. Our goal is to implement rigorous logic that cleans these inbound finding streams before record creation occurs. We achieve this by defining deduplication keys that act as a fingerprint for a unique issue. By leveraging hash creation criteria, we can transform metadata, such as the configuration item reference, the vulnerability ID, and the scanner-provided port information into a consistent value. This constant value is what the platform uses to perform lookup operations before deciding whether to perform an insert or an update. Configuring these unique constraint parameters requires a deep understanding of your specific scan tool behavior and your asset identification strategy. Many administrators fall into the trap of using overly simplistic keys, which leads to split finding errors where a single vulnerability appears as two distinct entities simply because a scanner reported a slightly different plugin output. To prevent this, we construct advanced composite keys that often include additional contextual data, such as the cloud-native resource ID or specific interface identifiers. When dealing with cloud-native resources, which are inherently ephemeral, simple hostname lookups are rarely sufficient. We must instead rely on immutable identifiers provided by the cloud provider API, which remain stable even if the underlying instance is rebooted or assigned a new internal IP address. This is the cornerstone of effective deduplication, and it requires careful planning of how you map external tool data to your internal configuration item repository. Another layer of control involves managing historical scan record convergence and update frequencies. When findings overlap across different scanning tools, we apply state reconciliation rules that prioritize the most granular or the most recent data point. This ensures that the system does not constantly flip the state of a record back and forth between closed and open if two scanners disagree on the patching status. We achieve this by establishing consistent tracking state behaviors that define which scanner holds the source of truth for specific attributes. Furthermore, we must optimize our lookup table index footprints, because if these tables grow too large without proper indexing, the validation logic will introduce significant latency during the import process. Indexing your deduplication keys is not just a best practice, but a necessity for high-volume ingestions coming from large-scale enterprise scan deployments. Ultimately, the goal is to establish a predictable mapping between your configuration assets and the vulnerability intelligence provided by external sources. You want to avoid a situation where a single configuration item has 10 records for the same vulnerability, as this destroys the value of your risk calculation and remediation efforts. By fine-tuning the deduplication logic, we ensure that the platform only creates a new vulnerable item record when it represents a genuinely unique security gap. This reduces technical debt in the form of administrative tasks required to merge closed or obsolete records. You should periodically review your reconciliation logs to surface any instances where potential duplicates escape the current filtering logic and adjust your composite keys accordingly. This iterative process acts as a quality gate, keeping your dataset clean and actionable for the security operations team. Carry this understanding into your next study session. Welcome back. In this session, we will examine the mechanics of the identification and reconciliation engine logs to understand how ServiceNow processes configuration data. When we discuss the identification and reconciliation engine, or IRE, we are essentially looking at the heart of the configuration management database integrity. The engine acts as a gatekeeper, determining whether incoming data from your vulnerability scanners or other discovery sources should create a new record, update an existing one, or be rejected entirely. When these transactions fail or behave unexpectedly, the reconciliation log becomes our primary diagnostic tool for uncovering the underlying cause. You will often find that the log output provides a serialized representation of the payload sent to the engine, which is the first place you should look when data fails to map correctly to a configuration item. By analyzing the identification results, we can see exactly which identification rules were triggered and why a specific rule might have failed to match even when you intuitively expect it to succeed. This process involves scrutinizing the input payload against the defined identification rules to ensure that the attributes you are providing match the hardware and software signatures registered in your system. If the identification engine reports a status of partial success or complete failure, it usually points to a mismatch in the unique attributes defined within your identification rules. Data execution exceptions often surface when the payload contains structural discrepancies that the engine cannot reconcile against the existing metadata. Imagine a scenario where two different discovery sources attempt to update the same configuration item simultaneously with conflicting data points. This leads to what we call data collision. The reconciliation log captures these events, showing us the specific source priority that won out and which source was sidelined during the update operation. Tracking these collisions requires a deep look at the source data and the reconciliation rules that dictate which source is considered the source of truth for specific attributes. Furthermore, we must address rule exclusion outcomes, where the engine skips a rule entirely because of preconditions that did not meet the requirement of the incoming data. If you notice logs indicating that a specific rule was bypassed consistently, it is likely due to the attributes within the payload missing mandatory fields that the identification rule requires for evaluation. This kind of diagnostic work is not just about troubleshooting errors. It is about refining the identification metadata so that the engine operates more effectively during the next sync cycle. Performance bottlenecks are an inevitable reality when dealing with massive reconciliation windows involving millions of configuration items. During these high-volume ingestions, the engine might spend excessive time evaluating complex identification rules, leading to latency that ripples through your vulnerability response dashboards. To diagnose these bottlenecks, you should analyze the execution timing logged within the reconciliation process, specifically looking for rules that consume a disproportionate amount of processing resources. Optimizing the identification payload is often the most straightforward solution, which involves pruning redundant attributes that do not contribute to the identification process itself. By keeping the payload lean, you reduce the memory overhead required for each identification event, which in turn speeds up the reconciliation engine's ability to process incoming vulnerability data. We often find that complex lookup criteria are the main culprits in slow execution, so simplifying these rules can drastically improve the throughput of your configuration data synchronization. Consistent analysis of these logs will reveal patterns in data volume that suggest when it is time to optimize the underlying CMDB structure or reevaluate the scheduling of discovery integrations. Building clean diagnostic reports starts with aggregating the raw data from the reconciliation logs and translating them into actionable insights regarding your data quality. You should focus on categories such as identification failures based on missing attributes, duplicate records created despite identification rules, and source-specific errors that indicate configuration issues in your vulnerability scanners. Once you have categorized these issues, you can create reports that highlight the most frequent offenders, allowing you to prioritize your cleanup efforts on the data sources that cause the most significant instability. A well-constructed report does not simply list errors. It categorizes them by severity and link, helping you maintain a pristine configuration database that acts as a reliable foundation for your vulnerability remediation processes. When you monitor these KPIs regularly, you shift your focus from reactive troubleshooting to proactive health management of your asset data. This disciplined approach ensures that when vulnerability scanners identify a new threat, the mapping between that vulnerability and the corresponding asset is accurate, reliable, and instantaneous. See you in the next lecture. Welcome back. Today we examine the life cycle of vulnerable items and how to maintain their state integrity within a ServiceNow environment. Vulnerable items are the granular units of work within the Vulnerability Response module, representing a specific vulnerability detected on a specific configuration item. Managing these records requires a clear understanding of the state model, which transitions through lifecycle stages such as open, under investigation, awaiting implementation, and closed. We must consider that these state transitions are not merely administrative labels. They often trigger business rules that execute critical logic, such as updating remediation targets or notifying assigned resolution teams. When designing these workflows, one must be cautious of how internal states interact with third-party scanner data streams, which frequently send updates back to the platform to synchronize status. If your logic is too permissive, an incoming integration payload might overwrite a manually updated state, effectively reverting hours of remediation work. Therefore, we utilize condition-based read-only constraints to lock records that satisfy specific criteria, ensuring data provenance remains intact during bulk processing. Data auditing becomes quite essential when dealing with such high-volume transactional records, as you need to track exactly who changed a status and when that change occurred. By structuring audit log retention rules, you ensure that the system does not bloat unnecessarily while still keeping a sufficient trail for compliance reporting. Programmatic record generation often relies on fields defined during the ingestion phase, and any discrepancy here can lead to orphans or incorrectly classified items. When you encounter a situation where a script trigger fails during a state update, the primary debugging path involves examining the asynchronous business rule queue to see if process threads are colliding. Managing record access locks is a necessary trade-off when multiple background batch updates occur in parallel, as you must prevent race conditions from corrupting the risk score or the assignment group. Establishing a robust set of closed conditions ensures that an item does not reach a terminal state without meeting the prerequisite security validations. I will see you in the next lecture. Welcome back. In this session, we will examine the mechanics of vulnerability risk calculators, focusing on how to quantify risk effectively within the ServiceNow environment. Vulnerability risk calculators are the engine room of your prioritization strategy, transforming raw data points into actionable risk scores. When you design these calculators, you are fundamentally defining what constitutes a critical threat to your unique infrastructure rather than relying on generic industry benchmarks. The framework operates on an evaluation hierarchy where multiple rules can be chained together, requiring a disciplined approach to ordering. If you set your order values incorrectly, you risk having a high-impact rule overridden by a broad, generic one, which effectively silences the precision you intended to achieve. Selecting the right criteria, such as business criticality, asset exposure, or environmental context, ensures that the resulting risk score aligns with the operational reality of your business units. This is not merely about setting a static number. It is about building a dynamic model that responds to the changing landscape of your CMDB and the shifting threat environment provided by your external security feeds. The logic governing these calculators relies on mapping specific conditions to impact and likelihood values. You should think of metric weighting profiles as the dial you turn to emphasize certain data points over others, such as giving more weight to a vulnerability located on an internet-facing server than one sequestered in a development network. When designing multi-criteria rules, you must remain conscious of nesting constraints that dictate how various rules interact within the calculation engine. If you create overlapping rules without clear boundary definitions, the system will struggle to determine which priority takes precedence, leading to calculation conflicts that frustrate your remediation teams. Always perform a trace on your calculations using the built-in diagnostic logs to verify that the system is arriving at the expected score based on the input parameters you have defined. A well-tuned calculator should be predictable, transparent, and defensible during an audit, as it serves as the ultimate authority for your remediation workflows. Performance tuning is a critical aspect of managing these calculators, particularly as your environment scales to include thousands of vulnerable items. If your calculation scripts are inefficient, you will notice delays in risk score updates, often manifesting as items stuck in the background processing queue. To mitigate this, ensure your calculation triggers are scoped appropriately to avoid unnecessary global recalc cycles that consume massive system resources without delivering value. When you encounter failures caused by missing data, implement validation steps that assign a default, unknown, or low risk score as a fallback, rather than letting the calculation fail silently or throw an error. Regularly clear out the calculation queue and monitor the diagnostic indices to identify the specific rule sets that are consuming the most execution time. By optimizing these background scripts and ensuring that your data ingestion layer provides clean input for the calculators to consume, you maintain high performance and high accuracy across the entire vulnerability lifecycle. See you in our next session. Welcome back. In this lesson, we explore the mechanical intricacies of the scoring engine within ServiceNow Vulnerability Response to ensure you can expertly normalize and calculate risk across your enterprise. The scoring engine acts as the central processor for risk quantification, shifting abstract vulnerability data into actionable business intelligence. At its core, the system relies on parsing vector strings, such as those formatted in CVSS version 3.1, into discrete numerical components. When a record arrives from a scanner like Qualys, it often includes a raw vector string. Your architectural task involves decomposing this string into its base metrics, including exploitability and impact subscores. This process requires a precise understanding of the formulaic relationships between attack vector, complexity, privileges required, and scope. If the system fails to parse these segments correctly, you introduce significant drift between the vendor-provided base score and your internal risk assessment. We manage this through script-based handlers that extract specific segment identifiers from the raw input block. Environmental score adjustments are where the platform truly tailors generic scanner data to your specific organizational context. By default, a vulnerability might carry a high base score, but if that software instance exists on an isolated network segment without business impact, your risk profile changes significantly. We implement internal risk calculators that apply weightings to variables such as the modified base score and the environmental score modifiers. These scripts evaluate the host configuration, looking for specific flags in the CMDB that signal high-value production assets versus development sandbox environments. You must ensure that these custom scripts possess proper error handling, as improperly formatted JSON or null pointer references during this evaluation phase can halt the entire processing pipeline for that specific vulnerable item. Temporal score metrics introduce the dimension of time and threat intelligence maturity into your calculations. While the base score remains static, the temporal metric fluctuates based on the availability of exploits or the efficacy of current remediation patches. In ServiceNow, you integrate these shifts by applying dynamic variables that influence the risk score calculation loop. When a new exploit moves from proof of concept to weaponized, the temporal score increases, effectively bubbling the corresponding vulnerable item to the top of your remediation queue. You are not just monitoring static fields. You are building an architectural framework that reacts to the evolving threat landscape in near real time. This dynamic rescoring is critical for maintaining an accurate posture regardless of how frequently your scanners run their discovery cycles. Third-party priority value normalization is a common point of architectural friction when dealing with multi-vendor environments. Diverse scanners express severity differently, often using proprietary scales that do not map cleanly to common vulnerability scoring system standards. To address this, we define normalization mappings that act as an abstraction layer between the raw source data and the unified internal score. We translate vendor-specific labels like urgent or critical into a uniform numeric target, typically ranging from 1 to 10, or a defined qualitative rank. This allows your remediation teams to view a single, consistent priority score regardless of whether the underlying data originated from Qualys, Tenable, or Rapid7. Achieving this uniformity requires rigorous testing of the logic maps to prevent truncation errors that occur when scaling floating point numbers during the normalization process. Finally, you must address the risk of mathematical truncation and data type inconsistencies within the underlying business rules. When performing complex arithmetic operations on vulnerability scores, the platform often defaults to integer rounding if the data dictionary is not correctly configured for decimal precision. These seemingly minor errors accumulate during large-scale ingestion processes, potentially leading to thousands of vulnerable items being categorized incorrectly. We solve this by explicitly casting variables within our script includes and validating the output of every mathematical transformation. By keeping the scoring logic modular and ensuring the input to output path is sanitized, we maintain the integrity of the risk score throughout the entire lifecycle of the vulnerability record. Proper architecture here is the difference between a high-noise environment and a high-signal security operations center that trusts its own data. I will catch you in the next lesson. Welcome back. Today we examine the mechanics of prioritization rule logic, an essential component for translating abstract risk into actionable remediation. In the ServiceNow Vulnerability Response module, prioritization rules function as the primary engine for determining which vulnerabilities demand immediate attention over others. When we construct these rules, we are essentially defining a business-aligned filter that interprets raw vulnerability data through the lens of institutional risk appetite. A well-constructed rule avoids the trap of assigning high priority to every item, which leads to operational fatigue and missed signals. Instead, we must leverage the interplay between asset metadata and threat intelligence to isolate what truly matters. If we treat every vulnerability as critical, we effectively treat none of them as critical, undermining the entire purpose of a structured response program. We need to define criteria that combine asset sensitivity with the likelihood of exploitation. Therefore, understanding the underlying Boolean logic and the order of operations in the rule evaluation table is non-negotiable for success. The foundation of effective prioritization rests on data fidelity, specifically how we link threat intelligence data to our vulnerable items. When configuring these rules, we often pull from threat intelligence tables that contain indicators such as exploit code maturity or evidence of weaponization in the wild. If we fail to properly configure these links, the prioritization engine lacks the context required to adjust risk scores dynamically based on the current threat landscape. We should focus on how these fields populate the vulnerable item records, ensuring the data is not just present, but searchable and filterable. For instance, an exploitable indicator should serve as a weighted trigger within our logic matrix, boosting the priority of a vulnerability regardless of its base CVSS score. This configuration ensures that a medium severity bug with a known active exploit is prioritized higher than a high-severity bug that remains theoretical or difficult to weaponize. Integrating business criticality requires us to look beyond the technical vulnerability and examine the asset itself within the configuration management database. We map the business service or the sensitivity of the data hosted on a configuration item to specific parameters within our prioritization logic. By doing this, we allow our rules to distinguish between a sandbox testing environment and a production database handling customer records. The logic must account for these distinctions by applying multi-layered filters that check against asset criticality tags or business service ownership. If we find that our current rules are misclassifying assets, we must inspect the Boolean matrices to determine if a conflict exists between conflicting, overlapping, or poorly sequenced filters. Often, the culprit is an overly broad condition that overrides more specific, high-intent policies simply because of the order in which the rules are processed by the system. Performance issues frequently arise when these rules encounter complex, slow-running filter queries during mass ingestion events. When we deploy heavy logic on large record sets, the system performance can degrade if the underlying database queries are not properly indexed or optimized. To troubleshoot this, we should analyze the execution time of the filter queries and look for scenarios where the logic branches are too deep or recursive. We must also be vigilant about missing threat feed variables, as an empty field in a lookup can cause a logic statement to evaluate to false unexpectedly. When we map threat trends against our infrastructure as part of an automated workflow, we have to ensure that the time-boxed constraints for elevation are applied consistently. These constraints prevent stale data from lingering in high-priority queues and ensure that the prioritization remains relevant to the current operational environment. Effective prioritization is an iterative practice that requires constant tuning and validation against the realities of your organizational infrastructure. By systematically verifying our Boolean logic matrices and ensuring clear communication between threat feeds and asset data, we create a resilient system that directs remediation efforts where they offer the greatest reduction in risk. Understanding these configurations allows you to confidently manage the flow of vulnerabilities, ensuring that your team spends their limited time addressing the most critical exposures first. See you in the next lecture. Welcome back. Today, we are shifting our focus to the programmatic evaluation of risk impact across your infrastructure. In the context of the vulnerability response module, impact assessment workflows serve as a bridge between technical vulnerability scores and business-level risk. While a raw CVSS score provides a baseline for a vulnerability's severity, it fails to account for the actual importance of the system it resides on. To truly understand the risk, you must consider the dependencies that exist within your configuration management database, or CMDB. When a system is compromised, the impact propagates through the business services that depend on that specific configuration item. We implement these workflows by defining how critical data flows through your technology stack, ensuring that if a core server fails, the platform recognizes that the dependent payroll or customer-facing applications are also at risk. Understanding these linkages is fundamental to moving from a reactive patching stance to a truly risk-aware vulnerability management program. Service mapping acts as the primary data source for these evaluations, providing the structure needed to traverse relationships between configuration items. When we configure impact assessment workflows, we are essentially telling the system to look up the dependency tree and aggregate the criticality scores of the services linked to a vulnerable item. If a virtual machine hosts a microservice that is part of a mission-critical web application, that vulnerability should carry a higher weight than one on a test server. The platform achieves this by calculating scores based on parent-child relationships, where the parent is often the business service or the application service itself. This cascading criticality ensures that the risk profile of an asset is not seen in isolation, but as a nested component within a larger, more critical architectural topology. We must be methodical about how we define these relationships to avoid inaccurate scoring that could lead to misguided remediation efforts. Configuring automatic business service dependency score modifiers requires careful attention to the nuances of your business logic and existing CMDB integrity. You might choose to apply a weight modifier that automatically elevates the risk score of vulnerable items if they are tagged as production-facing or part of a customer-sensitive data path. This logic is handled by setting up specific calculators that interpret these relationship flags during the initial assessment of a vulnerability. Another dimension involves tracking security exposure vectors, where we look at how data traverses through shared microservice topographies. If a single database supports 10 different services, its compromise affects all of them simultaneously, and our workflow must aggregate this risk magnitude accordingly. Efficiently tracking this requires us to prioritize relationship types that represent direct dependencies, often ignoring or filtering out noise that could skew the criticality upwards without justification. In many real-world environments, hard-coded calculation logic often fails to account for unique manual business requirements, necessitating the use of business impact overrides. These overrides allow security analysts to manually elevate or mute the impact score of specific assets, bypassing the automated calculations in scenarios where the context warrants an exception. However, relying too heavily on manual overrides undermines the predictability of your security posture across the enterprise. When you find that service traversal scripts are failing or yielding unexpected results, investigate the underlying relationship structures first. Often, a broken script is just a symptom of a missing relationship or cyclic dependency in the CMDB, which confuses the calculation engine during its traversal. The goal is a clean, immutable dependency model where the automated workflows can run consistently without human intervention to fix the risk profiles after the fact. To ensure the accuracy of your service risk profiles, you might need to engage in periodic troubleshooting of your cross-table evaluation structures. This involves validating that the connections between your vulnerability items, configuration items, and service offerings remain consistent over time. If a relationship flag goes missing during an asset import or an update, the upstream impact calculation will return an incomplete score, potentially leaving a high-risk vulnerability improperly deprioritized. You should audit your mapping logic by verifying that the traversal path accounts for both physical hardware and logical application services simultaneously. A robust system relies on real-time accuracy, which means your workflows must be triggered by any changes in the CMDB that affect the dependency tree. Ensuring that these updates propagate efficiently prevents the delay between an asset change and the subsequent security impact reevaluation. This concludes our overview of how to structure and maintain impact assessment workflows within the platform. I will see you in the next lecture. Welcome back. Today we examine the technical mechanics of optimizing high-volume risk recalculation loops within the vulnerability response environment. When we deal with multi-million record tables, standard script logic often becomes the primary bottleneck for system performance. The risk calculator must evaluate myriad variables for each vulnerable item, creating a computational load that scales linearly or even exponentially if queries are not curated correctly. We must begin by isolating the database execution paths that the engine traverses during a recalculation event. Often, a script will perform a glide record query inside a loop, which is a classic anti-pattern that triggers an individual database round trip for every single record in the batch. Instead, we should collect all necessary identifiers first and perform a single aggregate fetch to minimize overhead. By reducing the number of round trips, we significantly lower the wait time for the database to return the requisite datasets for our risk scores. Index management remains a cornerstone of efficient data retrieval in any relational database structure. If the calculation loop references fields that lack appropriate indexing, the platform is forced to perform a full table scan for every individual update. You should verify that the fields used in your filtering logic for risk calculators are covered by specific, non-overlapping indexes. Furthermore, take note of the synchronous versus asynchronous trigger mechanisms influencing these jobs. Synchronous triggers pause the user interface, which is rarely acceptable during massive update waves in a production environment. By offloading these tasks to asynchronous workers via the platform's background processing queues, we can govern the flow of work more granularly. This separation of concerns ensures that the platform remains responsive regardless of the ongoing volume of risk calculations. Chunk size control is the most direct lever we have to prevent transaction timeouts during large-scale operations. If we attempt to process 10,000 records in a single transactional block, we are almost guaranteed to hit the database duration limits. By implementing a chunking strategy, we break the larger update wave into manageable batches, perhaps 1 or 200 records at a time. This approach allows the system to periodically clear its cache and commit transactions, thereby avoiding the dreaded deadlocks that occur when multiple threads contend for the same data rows. Within these chunks, we must ensure that our parallel processing workers are configured to respect the platform's throttling limits. A well-tuned system keeps the processor busy without starving other critical background tasks of their compute cycles. Finally, we must tune the underlying system properties that manage these update jobs to guarantee performance during high-stress periods. Resource allocation settings define the maximum capacity for background workers, and these should be balanced against the overall footprint of your ServiceNow instance. In a security crisis where recalculations might trigger for entire hardware categories, the default settings often prove insufficient. We need to monitor the duration of these jobs using the Log Diagnostics to identify exactly where the latency manifests. If we see timeouts, we adjust the batch processing script logic or increase the worker thread pool size while keeping an eye on the CPU utilization across the node cluster. Maintaining this balance ensures that our risk posture remains accurate and up to date without compromising the integrity of the database itself. I will see you in the next lecture. Welcome to the module on vulnerability groups, where we dive into the structural mechanics that turn raw lists of vulnerable items into manageable workstreams. This chapter will provide you with the essential architectural knowledge required to master ServiceNow's grouping engine. In this lesson, we will focus on the architectural implementation of vulnerability groups. which serve as the primary containers for remediation efforts within the platform. At its core, the Vulnerability Group Table, or N or SOR VUL Vulnerability Group, acts as a parent record that logically aggregates numerous vulnerable items based on defined criteria. Understanding this structure is critical because it dictates how work is distributed across security and infrastructure teams during a remediation campaign. Unlike raw vulnerable items, which are often numerous and fragmented, groups provide a coherent unit of work that aligns with organizational change requests or patch deployments. You should view this relationship not just as a visual container, but as a rigid data model that interfaces directly with the ServiceNow task engine. When we architect these groups, we must account for the parent-child relationship complexity inherited from the standard task table, which allows for tiered remediation efforts. Improper configuration at this level often leads to significant performance degradation during large-scale ingestion processes, where thousands of items might be processed simultaneously. By mastering the underlying schema of these records, you gain the ability to predict how automation rules will trigger during integration runs. The creation of these groups is primarily driven by automation rules, which act as the engine room for grouping logic. These rules evaluate specific criteria, such as vulnerability, severity, assigned business service, or configuration item classification, before injecting records into the grouping table. When you configure your criteria, you are essentially setting the boundaries for what constitutes a manageable unit of work within your specific ecosystem. It is vital to recognize that the automation rule processor operates on a systematic schedule, evaluating the pending state of ingested vulnerabilities against existing group definitions. If a vulnerability item does not fall into a predefined group, the system retains it as a standalone record until a new rule or manual intervention reconciles it. You must also be cautious about the synchronization logic that links the group state with the underlying vulnerability item state. When a child vulnerable item is closed, the platform must determine whether to propagate that status change upward to the parent group. This logic is managed through business rules and flow triggers that maintain structural integrity across the entire vulnerability infrastructure. Managing structural integrity requires a clear head when dealing with potential configuration traps such as recursive loops or empty group generation. A common maintenance headache occurs when poorly constructed rules attempt to group items that are already inside another group, creating nested or circular references that the system cannot resolve. When building your criteria, ensure that your filtering logic is mutually exclusive or follows a clear hierarchy to avoid these runtime traps. Another issue that often surfaces during massive remediation campaigns is the accumulation of abandoned grouping records that lack active vulnerable items. These records clutter your dashboards and can lead to misleading metrics regarding your organization's risk profile. You should implement routine cleanup jobs that specifically target empty or inactive groups to keep the database footprint lean. Furthermore, when syncing groups with external ITSM change requests, ensure that your parent-child synchronization logic accounts for the latency between security updates and IT operational task completion. This focus on architectural hygiene ensures your vulnerability response platform remains a high-performance tool rather than a source of operational noise. See you in the next lecture. Welcome back. In this session, we will examine the mechanics of automated assignment rules within vulnerability response. When we talk about automated assignment, we are essentially building a decision engine that maps incoming vulnerable items, Vs, to the correct remediation teams. Standard assignment rules often rely on simple conditions, but in enterprise environments, we frequently need to interface directly with the Configuration Management Database, CMDB, to extract ownership data. By utilizing assignment rules, we can evaluate a VI based on its associated configuration items, CI, properties, such as the Managed by Group, Support Group, or even the department of the business owner. This requires a robust understanding of how to script dynamic field lookups using the assignment rule script field, which is executed when a rule matches. Rather than hard-coding static group assignments, you should aim to write reusable scripts that query the CI hierarchy to identify the legitimate endpoint owner. This approach minimizes administrative overhead because the assignment logic remains functional even when organizational structures or ownership metadata change within the CMDB. The engine behind these rules processes records in a specific order defined by the rule's execution sequence, which is a critical detail for implementation. If you have multiple rules that could potentially apply to a single VI, the system evaluates them according to their order value, stopping as soon as the first match is found. This makes the order field a primary tool for controlling logic flow, where more specific criteria, such as those targeting a specific OS or asset tag, must reside at the top of the pile. A common failure pattern occurs when high-order rules have overly permissive conditions, effectively shadowing or blocking more granular rules that you intended to handle specialized assets. Always audit your rule set to ensure that your sequence numbers reflect a hierarchy from most specific to least specific. If a VI bypasses all rules, or if your script logic fails to return a valid group reference, you encounter what we call null target routing, which leaves the VI in an unassigned state and delays remediation. To handle these gaps in logic, we implement fallback routing profiles that serve as a safety net when primary ownership lookups yield no results. A fallback mechanism might involve assigning a residual set of VIs to a generalist security triage queue, or perhaps performing a secondary lookup against a broad technical service owner instead of a specific CI owner. Within the script field, you can nest try-catch blocks to ensure that if a lookup for a specific CI owner fails, the script continues to traverse the relationship structure until it finds a valid assignment group. Effectively utilizing this strategy allows the system to remain resilient to missing or orphaned data in the CMDB. Furthermore, we must consider the performance implications of these scripts, given that they execute during every insertion or update of the vulnerable item records. Efficient scripts minimize glides, record lookups, and avoid redundant database hits, which keeps the total processing time per VI within an acceptable threshold. Troubleshooting these assignments requires a disciplined approach to log tracing, which is often underserved during initial setup. When an assignment seems incorrect, you should use the ServiceNow session logs or specific debugging variables to capture the path taken by the rule engine. By logging the evaluation results of individual conditional checks, you can quickly identify which rule matched, whether the script executed successfully, and what the final return value of the group assignment was. If you observe that a VI is being constantly reassigned between conflicting groups, it is highly likely that your filter conditions are not mutually exclusive or that multiple rules are matching the same record due to overlapping logic. I suggest maintaining a clean set of assignment rules where each rule is responsible for a distinct category of liability. By rigorously validating your assignment matrix against a sample set of production data, you verify that your routing logic handles both standard assets and edge cases without error. See you in the next lecture. Welcome back. In this chapter, we focus on service-level agreements within the context of vulnerability response, ensuring that your remediation timelines align precisely with organizational risk appetite. Service-level agreements, or SLAs, in the ServiceNow Vulnerability Response module, act as the primary governance mechanism for tracking remediation progress. While many developers are accustomed to SLAs in standard IT service management, the implementation within vulnerability response requires a deeper focus on risk-based prioritization rather than simple request fulfillment. We must define start, pause, and stop conditions that reflect the underlying reality of the security landscape. A start condition might trigger when a vulnerable item is created with a specific risk score, while a stop condition occurs once the vulnerability is verified as patched or mitigated. The pause condition is particularly critical in security operations, often triggered when a remediation task is awaiting third-party vendor validation or when an asset is undergoing scheduled maintenance that prevents patching. By carefully tuning these parameters, we ensure that the system holds teams accountable for remediation tasks based on the actual severity of the threat rather than arbitrary ticket age. To make these SLAs operationally significant, we must integrate them with the underlying business calendar and duration calculation rules. Unlike standard tickets, vulnerability remediation is deeply tethered to severity rankings. For example, a critical rated vulnerability usually demands a much tighter remediation window than a low-risk finding across non-production systems. We achieve this by mapping target definitions directly to the risk score ranges evaluated by your vulnerability calculators. When an SLA breaches, it should act as a signal that the corporate risk policy is at stake, necessitating an automated escalation trigger. This usually involves activating a flow that notifies the relevant security leads or management stakeholders, ensuring that remediation bottlenecks are addressed before they become significant audit findings. Configuration of these warnings often happens through threshold notifications, which provide a proactive alert before the deadline is actually reached, allowing the incident owner to request an extension or prioritize the task effectively. Troubleshooting the SLA engine becomes an unavoidable responsibility when dealing with complex global infrastructure. One of the most common pitfalls involves time zone discrepancies, where an SLA based on the system clock might miscalculate the actual deadline for a team operating in a different region. We resolve this by ensuring the business calendar is correctly associated with the assignment group's schedule rather than the instance's default setting. Another frequent pain point is the evaluation of pause conditions, which can stall if the script logic is too rigid or relies on fields that are frequently overwritten by integration processes. When you encounter unexpected calculation behavior, inspect the SLA engine background jobs to determine if the processing queue is congested, preventing timely updates to state fields. Optimizing these jobs often involves refining the filter conditions so the engine only evaluates items that truly require a state change, rather than re-indexing every open task on every update. By maintaining clean, logical, and performant SLA definitions, you transform the vulnerability response module from a reactive tool into a reliable measure of your security posture. I will see you in the next lecture. Welcome back. Today, we are delving into exception management workflows to ensure your vulnerability program remains both compliant and agile. We will focus on how to govern deferred items effectively within the ServiceNow ecosystem. In any mature vulnerability response program, there will inevitably be scenarios where immediate remediation is technically impossible, economically unfeasible, or operationally disruptive. Rather than leaving these vulnerabilities in an open state, which would artificially inflate risk metrics and distract technical teams, ServiceNow provides a structured framework for exception management. This process allows security teams to formally request a temporary stay of remediation, provided they supply sufficient justification and secure the necessary approvals. By utilizing the Vulnerability Exception module, organizations can maintain a clear audit trail that links technical risks to governance, risk, and compliance frameworks. Understanding how to model these workflows is essential for any professional managing vulnerabilities at scale, as it moves the practice from ad hoc emails to a system of record. Configuration begins with the application form, which acts as the intake mechanism for any deferral request. It is vital to define exactly what data is captured during this submission, as this metadata, such as the business justification, the requested expiration date, and the specific risk acceptance criteria, will later be used to drive approval logic. Once a request is submitted, it does not simply move to a state of approval. It must be funneled through a hierarchical routing rule. These rules can be built based on the criticality of the CI, the business unit, or the underlying risk score of the vulnerable item. By leveraging ServiceNow's approval engine, you can ensure that the right stakeholders, such as asset owners or GRC managers, have the final say before an exception is granted. Time-bound deferrals represent the next core component, as every exception must possess a finite lifespan to prevent set and forget security debt. When an exception is created, the system must be configured to track the expiration date, which triggers an automated reactivation of the underlying vulnerability record once that threshold is crossed. This auto-expiration logic is critical because it forces the organization to perform an annual or periodic review rather than allowing risks to remain masked indefinitely. Furthermore, false positive tracking serves as a specialized form of exception where the vulnerability is not deferred, but rather flagged as non-applicable. Proper handling of these false positives involves metadata tagging that ensures the vulnerability scanner does not simply re-ingest and reopen the same issue in the next scan cycle. To ensure the technical integrity of these workflows, we must address the common pitfalls that lead to state transition stalls or broken authorization scripts. Often, an exception workflow fails because the logic assumes a static path, whereas a robust implementation must account for multiple approval stages that may change based on dynamic inputs. If an exception requires both a technical lead and a risk officer, The workflow designer must use parallel or sequential flows that gracefully handle rejections or modifications. If these scripts are not written to explicitly handle empty or malformed return values, the entire remediation process can hang, leading to data staleness. By modularizing your authorization logic and adding validation overrides for emergency situations, you create a system that is resilient to organizational changes and process anomalies. Audit history preservation remains the final, yet arguably most important aspect of the exception lifecycle. Because these deferrals represent a conscious decision to accept risk, you must maintain an immutable record of who authorized the exception, why they authorized it, and what compensating controls were implemented to mitigate the gap. ServiceNow allows for the capture of these snapshots through field auditing, but it is best practice to associate these records with specific GRC policy linkages. When an auditor asks why a particular server remained unpatched for a quarter, your system should provide not just the exception record, but the lineage connecting it to the broader organizational risk appetite. This structural transparency is the hallmark of a high-maturity vulnerability response environment. See you in the next lecture. Welcome back to our exploration of the vulnerability response ecosystem. Today, we focus our attention on the lifecycle management of remediation tasks. In the ServiceNow Vulnerability Response architecture, a remediation task acts as the container for actionable security work derived from one or more vulnerability groups. While vulnerability groups provide the logical grouping of similar risks, remediation tasks represent the actual unit of effort assigned to a technician or remediation team. Understanding the mechanics of these tasks requires us to look at how record generation properties interact with consolidated vulnerability data. When you manage these tasks, you are essentially defining the bridge between a security finding and the physical act of patching an asset. It is important to realize that the lifecycle of these tasks is governed by specific state synchronization rules that ensure the work performed is accurately reflected across the entire system. One of the most complex areas of remediation task management is the configuration of split-merge logic. When vulnerabilities are grouped, the system uses specific criteria to determine if a vulnerability should remain within an existing remediation task or trigger the creation of a new, separate task. If you modify the underlying grouping rules, you must be aware of how the system handles existing records to avoid orphan tasks or duplicates. Imagine a scenario where a high-severity vulnerability is added to a workstation group mid-cycle. If your merge logic is misconfigured, it might inadvertently bypass your standard validation workflows. Proper configuration ensures that tasks remain maintainable while preventing the fragmentation of vulnerability data into thousands of unmanageable microtickets. Validation and verification workflows are the components that safeguard the integrity of your security posture before a task is considered truly closed. Most organizations implement automated triggers that verify the completion of a task based on subsequent clean scanner ingestion data. When a scanner performs a fresh discovery and no longer identifies the original vulnerability, the system can automatically mark the associated remediation task as verified. However, this automation must be carefully structured to prevent accidental mass closure if a scan fails, or if the data ingestion process encounters an error. You should design these verification triggers to validate both the presence of the vulnerability and the current status of the affected configuration item. Managing technician state updates requires a firm grasp of how state synchronization moves from the task level back to the underlying vulnerable items. When a technician updates a remediation task status to work in progress or resolved, this information must flow correctly through the hierarchy to ensure consistency. Mismatches often occur when manual updates are applied to vulnerable items that are currently locked by an active remediation task. You must configure your cascading behaviors so that closing a parent task appropriately influences the child records, preventing inconsistent data states. Debugging synchronization failures involves examining the business rules and scripts that enforce these transitions, ensuring that state transitions are unidirectional and predictable. Finally, we must consider the risk of accidental mass closure, which can happen if automation logic is too aggressive. Security teams often prefer a closed-loop approach, where the system monitors progress and only pushes updates when specific criteria are confirmed. When you structure parent task close cascading behaviors, Ensure that you have safeguards in place to require manual sign-off for critical production assets. This acts as a final gatekeeper, ensuring that automated logic has not misinterpreted a network-related scan failure as a successful patch deployment. By maintaining clear separation between discovery data and remediation status, you create a robust workflow that supports both security and operational stability. I look forward to seeing you in our next session on architectural diagnostics. Welcome back. In this lesson, we will focus on diagnosing and resolving performance bottlenecks that arise during the evaluation of automated grouping rules and assignment processing scripts. When we discuss grouping performance within the vulnerability response module, we are essentially looking at the efficiency of the background engine that processes large volumes of vulnerable items. As the scale of your infrastructure grows, the logic used to group these items, often relying on complex condition sets, can inadvertently impose significant overhead on the system. The primary goal is to ensure that the grouping engine does not stall during high-throughput influxes of vulnerability data. We often see issues where rule evaluation paths become overly convoluted, requiring the engine to perform millions of operations per second just to evaluate if a single vulnerable item belongs to a specific group. Analyzing these evaluation paths requires a disciplined approach, usually starting with an examination of the business rules and scripts triggered during the insert or update of a vulnerable item. If you find that the system is spending disproportionate time on rule resolution, it is time to look at the complexity of your scripts. Table scanning is a classic performance trap that manifests when your grouping conditions are not properly supported by indexed fields. If an automated grouping rule specifies a condition on an unindexed field, the database engine is forced to perform a full table scan for every single vulnerable item processed. This is exponentially expensive as your vulnerability table grows. Imagine querying a million records where the database has to touch every row because there is no index to prune the search space. The result is a massive performance degradation that ripples through the entire background worker pool. To mitigate this, you must ensure that all fields used in your grouping rule filters are indexed appropriately. You should frequently review the system logs to identify queries that exhibit high execution times, as these are often indicators that the database cannot resolve the filter path without a full scan, ultimately causing locks that delay other critical tasks. Sometimes the issue is not the lack of an index, but rather how we invoke our queries through script. Highly complex encoded query strings within grouping definitions can often be deconstructed into simpler, more atomic operations. When a script runs, it effectively becomes an extension of the system's background processing capacity. And if that script is inefficient, it steals cycles from other essential background jobs. We need to be careful with how we handle batch size parameters, as pushing too many updates into a single transaction can lead to lock contention, where one process waits for another to finish its write operation. Managing worker threads is equally critical in this context, as having too few workers creates a queue backlog, while too many might lead to resource exhaustion. By tightening the batch sizes, we allow the system to process items in more manageable, consistent chunks, which improves throughput and prevents the dreaded background script timeouts that halt remediation workflows. Ultimately, optimizing high-throughput task routing involves a balance between the precision of your grouping rules and the raw compute capability available. We must be surgical when we implement scripting, avoiding heavy calculations inside loops that iterate over large record sets. Instead, look for ways to leverage pre-calculated data points or use asynchronous processing to prevent the user interface from locking up during mass updates. Monitor the duration of these background scripts closely. If you see recurring timeouts, you are likely hitting an architectural limit that requires a restructuring of the rule logic itself. Remember that every millisecond shaved off a grouping rule execution is a millisecond gained in the overall speed of your vulnerability remediation lifecycle, which is the ultimate metric of success in a mature deployment. Keep your logic lean and your indexes relevant, and the system will remain performant even under significant load. I will see you in the next session. Welcome back to our exploration of the ServiceNow Vulnerability Response ecosystem. In this session, we will examine the mechanics of implementing Flow Designer specifically for the unique demands of vulnerability remediation workflows. When we construct automation in the context of security operations, we are essentially codifying the incident response lifecycle into a repeatable, deterministic state machine. The Flow Designer provides a robust abstraction layer over the traditional workflow engine, allowing us to define trigger conditions that strictly monitor incoming vulnerable items or state transitions. A trigger in this environment is not merely a signpost. It acts as a gatekeeper that ensures our automation logic only executes when specific criteria are met, effectively reducing the noise of unnecessary processing cycles. By leveraging condition-based triggers, we maintain strict control over performance, as the system will ignore events that do not align with our predefined security thresholds. This approach is superior to older scripting methods because it visually maps the logic flow and maintains clear boundaries between data inputs and automation outcomes. We must prioritize these triggers carefully, as overlapping conditions can lead to race conditions or duplicate remediation requests that complicate audit trails. Proper trigger design is the foundation upon which all subsequent automated remediation efforts reside. To facilitate complex logic, we often rely on custom flow actions that encapsulate modular pieces of functionality, such as querying external patch management databases or updating asset risk scores. These actions should ideally follow the principle of low coupling and high cohesion, meaning each action serves a single, well-defined purpose within the larger orchestration. Inside these actions, we utilize script step components to bridge the gap between low-code configuration and complex programmatic requirements that standard flow steps cannot handle. When writing these scripts, one must be cautious about the global scope and ensure that our data transformations within multi-stage loops do not inadvertently degrade engine performance. A loop processing thousands of vulnerable items can quickly consume available memory if we are not careful about how we handle collections and object references. We need to implement flow variable architectures that persist data across different stages of the flow, allowing for clean state management without relying on static global variables. This design pattern ensures that our architecture remains maintainable and testable over the long life cycle of the vulnerability program. Inevitably, even the most carefully designed automations will encounter runtime exceptions, which necessitates robust error trapping within our flow blocks. ServiceNow provides error handling blocks that allow us to define specific pathways for logic failures, such as a failed API call to a deployment tool or a timeout during an asset lookup. Using these blocks, we can gracefully revert state changes, log the specific incident to a diagnostic table, and trigger alerts for human intervention. Without explicit error trapping, a flow might simply hang in an indeterminate state, leaving vulnerable items orphaned in a mid-remediation status. We should also leverage flow design versioning to manage these configurations, ensuring that we can revert to a known good state if a deployment introduces unexpected behaviors. Tracking execution states via the flow context allows us to audit the entire path taken by a specific vulnerable item, which is a critical necessity for compliance reporting. By proactively managing how our flows handle errors and versioning, we ensure that the Security Operations Center remains informed even when the automated infrastructure encounters a hurdle. Finally, let us consider the optimization of flow engine resource usage and the security of our data streams. In multi-scope environments, it is essential to manage access correctly so that flows do not inadvertently expose sensitive vulnerability information to unauthorized applications or users. We must configure the flow runtime to adhere to the principle of least privilege, ensuring each flow context only has the permissions necessary to perform its specific task. When flows run in parallel, we must be cognizant of the resource implications on the instance, particularly regarding transaction quotas and memory utilization. This involves tuning our design to avoid overly broad triggers and optimizing database queries executed within script steps to prevent long-running transactions. Periodic review of the execution logs will reveal bottlenecks or inefficient loop operations that can be optimized through caching or more selective result filtering. By maintaining these standards, we build an automation resilient enough to scale with the ever-increasing volume of vulnerability data that modern organizations face. Trust this provides a solid understanding of how to configure automated flows for vulnerability remediation. See you in the next session. Welcome back. In this lesson, we explore the mechanics of integrating vulnerability response with the IT Service Management Suite to bridge the gap between security detection and operational remediation. When we discuss ITSM remediation integration, we are primarily concerned with creating a reliable, transactional bridge between a vulnerable item and the broader IT operational ecosystem represented by incidents and change requests. The fundamental challenge is maintaining data integrity while ensuring that security-driven tasks translate meaningfully into the existing workflows used by system administrators and platform engineering teams. We start by configuring how vulnerability records trigger ITSM objects, which usually involves defining clear mapping rules for fields such as assignment groups, priority levels, and short descriptions. It is a mistake to treat this as a simple copy-paste operation because the requirements for a security ticket differ substantially from a standard operational request. We must ensure that the mapping logic accounts for the specific nuances of the vulnerability, including its severity and the asset criticality identified within the CMDB. If we fail to establish this mapping correctly at the outset, we introduce significant friction for the teams tasked with the actual patching or remediation work. By standardizing these field cross-mappings, we create a predictable output that allows IT staff to act upon incoming tickets immediately without needing to hunt for context in external vulnerability dashboards. Beyond simple metadata mapping, we need to focus our attention on the real-time synchronization of state and activity streams between these two domains. Without a robust, event-driven architecture, updates made to a change request might never propagate back to the vulnerable item, leaving security analysts in the dark about the actual status of an ongoing remediation. We implement this through business rules or flow designer triggers that watch for state changes, ensuring that when an IT change request moves to a closed or resolved state, the associated vulnerability group or individual vulnerable item is updated accordingly. However, we must introduce safeguards against infinite update loops, where a change in an IT record triggers an update to the security record, which in turn cascades back into the IT record. This usually manifests when developers perform blind field writes without checking for existing values or utilizing flags to prevent the synchronization logic from refiring its own triggers. By tracking the execution context and properly utilizing the update record methods that bypass specific business rules, we maintain a clean and performant transactional flow that keeps all stakeholders aligned without corrupting the operational audit trail. Finally, we address the specialized logic required for emergency incident generation versus standard patch rollouts. For zero-day threats or high-velocity vulnerabilities, we often configure immediate incident creation to bypass standard change calendars and expedite the remediation process. This involves setting specific triggers that look for defined risk thresholds, automatically creating high-priority incident records, and applying unique close-code behaviors that signify a successful security patch. We want to avoid polluting the system with redundant or poorly formatted tickets, so the automation must be conditional and context-aware, filtering only for assets that are production-critical or currently exposed to active exploits. When the remediation is complete, we perform a reconciliation process that validates the closure of both the security and IT tasks. This entire integration strategy must prioritize visibility and auditability, as security compliance often hinges on the ability to prove that every vulnerable item was not just identified, but effectively mapped to a documented, verified, and successfully closed operational task. See you in the next lecture. Welcome to this exploration of patch orchestration, where we will translate vulnerability identification into actionable remediation through external platforms. In this chapter, we focus on the mechanics of connecting ServiceNow Vulnerability Response with external patch management systems using Integration Hub. Effectively automating patch deployment requires a deep understanding of how to map vulnerable items to specific deployment groups and how to manage the lifecycle of a patch task. We will move beyond simple integration to master the construction of API payloads and the verification of deployment metadata. By the end of this journey, you will possess the expertise to build robust orchestration flows that handle complex deployment scenarios and resolve common integration failures. This knowledge is essential for passing the certification exam and for delivering true security value in a modern enterprise environment. Patch orchestration configuration represents the bridge between knowing what is vulnerable and actually mitigating that risk within your production infrastructure. When we talk about orchestration in this context, we are primarily concerned with using Integration Hub to communicate with third-party tools like Microsoft Endpoint Configuration Manager, Tanium, or big fix. The configuration starts by defining how vulnerability groups act as the source of truth for your patch requirements. You must ensure that your target assets are accurately reflected in the configuration management database, as the orchestration engine relies on these CI records to determine the correct target scope for any given patch command. We are essentially automating the process of sending granular instructions to an external executor, and that requires a rigorous definition of data mappings between the vulnerable item and the external deployment entity. The heart of this automation is the API payload construction, which requires meticulous attention to the schema expected by the remote deployment server. When you configure your Flow Designer actions, you are crafting a structured data object that must contain precise identifiers for both the target asset and the required patch package. If your mapping logic sends a malformed payload, the remote system will inevitably reject the request, resulting in a failed deployment task and a breakdown in your remediation chain. You should leverage the Integration Hub input variables to dynamically populate these payloads, ensuring that every deployment request is uniquely tied to a specific vulnerable item or group of items. Always include validation steps within your flows to check if the necessary metadata, such as patch identifiers and asset GUIDs, is present before the payload is ever transmitted outbound. Verification of deployment package metadata is not merely an optional step. It is a critical defensive measure against inadvertent misconfiguration. Before you finalize a patch deployment, the orchestration logic should perform a pre-flight check to verify that the target system is compatible with the patch version you are requesting. This involves comparing the vulnerability metadata received from the scanner feed against the current configuration state of the CI stored in the CMDB. If the metadata is unreliable or missing critical version numbers, your automation should treat this as an exception rather than proceeding blindly. By implementing these checks, you establish a feedback loop where the system can proactively identify if a patch is irrelevant or potentially detrimental before a command is ever logged against an asset. Tracking deployment task progress requires an integration design that favors asynchronous communication and robust polling mechanisms. Once you have pushed the command to your orchestration target, you should not assume the task succeeds. Instead, you must maintain a stateful record of the deployment task within the vulnerability response module. This usually involves querying the external server for a status update at specific intervals using a wait-for-response pattern in Flow Designer. If the external system returns a success state, your flow should update the corresponding vulnerable item to reflect the new remediation status or trigger a reassessment loop. If the response indicates a failure, your orchestration should automatically log the response codes and potentially escalate the issue to the security operations team for manual investigation. Handling errors gracefully is perhaps the most important aspect of building a resilient orchestration ecosystem, particularly when dealing with heterogeneous environments. Endpoint connection errors are an inevitable reality when integrating with global patch deployment servers, so your flows must be designed to handle timeouts and network partitions without crashing the entire state machine. You should implement custom error handlers in your subflows that catch these diagnostic events and record them in the vulnerability log history. When you encounter a failed deployment, analyze the specific return codes provided by the third-party API to determine if the issue is a transient network glitch or a structural problem with the command itself. By logging these historic patterns, you gain the visibility necessary to tune your timeout thresholds and improve the overall reliability of your automated pipeline. See you in our next session. Welcome back to our exploration of advanced automation within the vulnerability response environment. Today, we are focusing on automated reassessment loops, which provide the mechanism for confirming that remediation efforts have actually succeeded. In any mature security operation, the gap between marking a vulnerability as resolved and actually confirming that the underlying exposure is gone represents a significant lifecycle risk. We rely on automated reassessment loops to bridge this gap, ensuring that our scanner integration performs a targeted verification scan once a remediation task transitions to a closed state. This process begins with the trigger definition, where we configure the system to monitor specific state transitions on a vulnerable item or a vulnerability group. When that state change occurs, the system must interact with the scanner's API to initiate a scan payload restricted to the specific configuration item affected. This targeted approach prevents the inefficiency of full network scanning, keeping our platform resources focused strictly on the scope of the original remediation activity. By isolating the scan request to the affected asset, we drastically reduce the processing overhead and network traffic, while simultaneously ensuring the highest possible accuracy for the verification result. Once the trigger fires, the orchestration logic enters a polling cycle that requires careful management of long-duration processes. We cannot simply hold an open connection to the scanner. Instead, we utilize persistent polling loop scripts that communicate with the integration hub to check the status of the scan task. This involves sending a request to the third-party scanner's API, receiving a manifest of the scan job, and parsing the post-scan success indicators returned by the provider. Because these scans can sometimes take hours, depending on the complexity of the asset and the network segment, we must implement robust timeout handlers. If a scan job exceeds the expected window, the system must be capable of failing gracefully or requeuing the task, ensuring that stuck verification states are automatically cleared after a defined period of inactivity. Effective integration requires a deep understanding of these callback mechanics, as the data returned from the scanner must be correctly mapped to the record state in order to update the vulnerable item automatically. Performance optimization remains a constant concern when implementing these loops because an aggressive polling interval can quickly lead to platform resource exhaustion. If your background scripts fire too frequently, you will consume worker threads unnecessarily, leading to contention that impacts other automated processes like incident creation or CMDB reconciliation. The optimal strategy involves a back-off algorithm where the polling frequency decreases if the scan is expected to take a significant amount of time, allowing the system to sleep between requests. Furthermore, we must account for scanner connection rejections, which often occur due to rate limiting or authentication token expiration in high-volume environments. Your error handling logic should not just log these failures, but should attempt to recover the session state without manual intervention. By constructing resilient payloads that include accurate asset identifiers and specific plugin signatures, we minimize the likelihood of receiving an invalid request error from the target scanner. When these components work in harmony, the closed-loop system creates a high-integrity audit trail that proves remediation effectiveness to stakeholders. You are not just closing a ticket because a developer claimed a fix was applied. You are closing it because the system has verified, through a targeted interrogation of the environment, that the vulnerability is no longer exploitable. This transition from manual verification to automated policy-driven validation is the cornerstone of a high-maturity security program. It alleviates the burden on your security analysts by filtering out false positives occurring after the fact, allowing them to focus on active threats rather than verification overhead. Mastering these technical loops ensures that your vulnerability response instance acts as a true automated platform, rather than merely a record-keeping repository for security data. As you configure these routines in your own environment, keep the focus on resource efficiency and programmatic error handling to ensure consistent, scalable performance across your enterprise infrastructure. I will see you in the next lecture. Welcome back, and today we turn our attention to the orchestration of security incidents. In this session, we explore the mechanisms for escalating critical vulnerable items into formal security incident records. When we approach the challenge of escalating a vulnerable item to a formal security incident, we must first consider the boundaries of the ServiceNow application scopes. Vulnerability response operates within its own dedicated scope, while security incident response, or SIR, resides in another. This architectural separation enforces security by default, meaning that a direct cross-scope update is not permitted without explicit application cross-scope access records. To facilitate this data transfer, we utilize cross-scope data mapping rules that define exactly which fields from the vulnerable item should be populated into the corresponding fields on the security incident record. Without these carefully configured rules, your automated scripts will fail to execute, leaving your security teams unaware of critical threats that require immediate intervention. The actual transition from a vulnerable item to a security incident is typically triggered by a business rule or a flow designer action that executes a target table record initialization script. This script acts as the bridge, ensuring that the payload, which might include sensitive data about the affected configuration item, the vulnerability vector, or the risk score, is transferred securely. We must treat this payload with extreme care because it often contains information that is subject to cross-department confidentiality controls. If a user does not have the necessary technical role or the correct departmental access, the platform will and should block the record creation. My recommendation is to always wrap your initialization scripts in a try-catch block to gracefully handle potential privilege access errors, ensuring that the system logs the failure rather than crashing the current thread during an automated workflow execution. Linkage tracking is an often overlooked aspect of effective security operations, yet it is vital for maintaining the integrity of your audit trail. When you spawn an incident from a vulnerable item, the system should store the SysID of the source record within a reference field on the target security incident. You should configure your logic to maintain this bidirectional linkage throughout the lifecycle of the security incident. This allows your analyst to navigate back to the original vulnerability analysis while keeping the vulnerability manager updated on the status of the investigation. If this link is broken, you lose the ability to perform automated status updates, forcing your teams to switch back and forth between modules manually. A well-constructed handoff procedure should update the vulnerable item status to a state like under investigation the moment the security incident moved to an in-progress status. Finally, let us discuss how to configure the escalation criteria themselves, which usually depend on detecting active threat exploit data within the vulnerability response environment. You should define your thresholds based on specific fields, such as whether an exploit code is publicly available or if the threat intelligence feed has flagged the vulnerability as part of a current campaign. These fields should be mapped into your orchestration logic to ensure that only truly emergent threats trigger the creation of a security incident. By focusing on these indicators, you prevent the inundation of the security team with false positives or low-priority items that do not require full incident response rigors. Always validate these criteria by simulating a vulnerable item update in your sub-production environment before moving the logic into your core production flow. See you in the next lecture. Welcome back. In this lesson, we will focus on the diagnostic techniques required to ensure your automated security flows remain performant and reliable within the vulnerability response ecosystem. When we observe an automation flow that either stalls or fails to produce the expected remediation outcome, our first instinct should be a systematic investigation of the execution context. Automation in ServiceNow often relies on complex chains of actions that pass data structures between steps, and identifying where these transfers break down is fundamental to stabilization. We begin by inspecting the flow execution logs, which act as our primary forensic evidence. These logs provide a record of every transaction, showing exactly where a flow might have entered in wait state or encountered a data type mismatch. By examining the context object, we can see if the expected variables are present or if a previous step has injected null values into the process. If a flow hangs indefinitely, we must check if an unintended loop or a deadlock has occurred due to recursive trigger conditions. Identifying these patterns often requires looking specifically at the sequence of execution and confirming that each branch has a clear termination point that the engine can identify. Analyzing step performance data points requires a disciplined look at the overhead introduced by integration points and external calls. Often, a flow is not strictly failing, but rather performing poorly because an action step is awaiting a response from an external source, such as an ITSM ticket update or a remote patch management server. We can use the platform's diagnostic tools to measure the duration of specific steps, which helps in isolating whether the delay is internal to the flow logic or external to the platform's capacity. If we find that a parallel execution branch is causing contention, we must consider re-architecting the flow to decouple these actions. Poorly designed parallel branches often create race conditions where the order of operations conflicts with the requirements of the downstream data processing. By flattening these structures or introducing explicit dependencies through flow variables, we can manage the state transitions more effectively and prevent the jamming of system context that occurs when resources remain locked for too long. Data type conversion issues represent some of the most subtle yet frustrating errors in automated flow design. When an action step passes data to a subsequent activity, the underlying type, be it a string, an integer, or a reference, must be treated with specific care to ensure the receiving step handles it as intended. Mismatched data types typically result in silent failures or input validation errors that prevent the automation from proceeding to the next logical step in the remediation chain. We should verify these transformations by comparing the output of the source action against the expected input schema of the target action. If the architecture permits, adding a validation step or an intermediate transformation script can often resolve these irregularities and ensure the flow remains robust against unexpected data entry. By treating every flow as a series of well-defined interfaces, we reduce our dependency on implicit behavior and increase the predictability of the security operations lifecycle. Integration transaction histories and error snapshots provide the necessary context to resolve failures that reside outside the flow designer itself. When an automation relies on an API call or a business rule integration, the vulnerability response context may appear fine, while the underlying interaction has faulted due to authentication issues or throttle limits. We must drill down into the transaction record associated with the specific execution to see the raw request and response data. If the response contains a non-standard return code, the flow may not have a defined transition to handle that specific scenario, leading to a jammed state. By clearing out these stalled contexts and refactoring the error handling paths, we ensure that the automation remains in a consistent state, even when external integrations fail. This proactive diagnostic approach effectively minimizes downtime and optimizes the reliability of the entire vulnerability remediation workflow. See you in the next lesson. Welcome back. In this chapter, we explore how to configure specialized performance analytics indicators and collection schedules to turn raw vulnerability data into actionable insights for your organization. Performance analytics in the context of vulnerability response allows us to move beyond simple list views and investigate the historical health of our security posture. To begin, we must master the configuration of indicator sources, which act as the foundational filters for the data collection process. An indicator source essentially defines a set of records, such as vulnerable items, that meet specific criteria at a given point in time. When you define these sources, ensure that the conditions are precise, as they dictate the scope for all downstream metrics. You should consistently leverage date-based fields such as the open date or close date to allow for meaningful time series analysis later on. By keeping these queries lean and indexed, you avoid unnecessary performance overhead on the platform during the periodic collection runs. Once your indicators are configured, you will inevitably need to categorize the data using breakdowns. Breakdowns provide the multi-dimensional perspective required to answer questions about which assignment groups or business criticalities are driving your vulnerability trends. When implementing these, consider using breakdown mappings, which link your indicator data directly to properties on the configuration item or the vulnerable item itself. If a standard field mapping does not suffice, we turn to automated breakdown mapping scripts to transform raw data points into actionable categories. For example, if you need to group vulnerabilities by a custom risk tier not natively available in the vulnerable item table, a script can inspect the associated CI class and return the expected bucket value. Always evaluate the complexity of these operations, as overly intricate scripts executed during data collection windows can lead to job timeouts or latency issues. Efficient data collection requires a disciplined approach to scheduling and job optimization. We often find that collecting data too frequently across too many indicators puts undue strain on the instance resources. I recommend aligning your collection jobs with the business requirements for reporting, ensuring they run during off-peak hours whenever possible. You can further optimize this by utilizing filter conditions within the data collector job to process only the records that have changed since the last run. Should you encounter failures, the job logs provide the necessary transparency into script processing errors or access control violations. When tuning these windows, think about the total volume of data under management and balance that against the frequency needed to maintain an accurate view of your remediation velocity. Another essential component in this toolkit involves the definition of bucket groups to categorize numeric data. Using bucket groups transforms continuous ranges, such as the age of a vulnerability in days, into discrete buckets like 0 to 30 days or over 90 days. This is crucial for tracking metrics related to service level adherence or risk aging. Defining these ranges requires collaboration with your stakeholders to ensure the thresholds align with the internal policies of your vulnerability management program. When configuring the bucket groups, Ensure your logic is exhaustive and mutually exclusive to prevent data gaps in your resulting analytics. A clean implementation of these groups allows you to visualize trends in a way that is easily interpretable for decision makers who do not necessarily need to view the raw underlying data. See you in the next lesson. Welcome back. Let us discuss how to measure and improve your organizational remediation velocity within the vulnerability response environment. In this section, we move beyond simple data aggregation to focus on the sophisticated reporting structures required to measure how quickly your organization responds to vulnerabilities. We will explore how to translate raw data points into actionable insights that reveal the true health of your security lifecycle and its operational efficiency. When we approach remediation velocity tracking, the core objective is to calculate the time elapsed from the identification of a vulnerability to its effective closure. This mean time to remediate, or MTTR, serves as the most critical key performance indicator for the security team. It is not enough to simply count closed items, because the duration of exposure, the time the threat exists within your infrastructure, is what truly defines the risk profile of the organization. To calculate this accurately, you must ensure that state transitions are strictly governed by your workflow, as the system relies on specific timestamps during the lifecycle of a vulnerable item. If your process allows for excessive time in states like awaiting implementation, you will find your metrics skewed, which necessitates a deeper look at your duration calculation formulas. We often see practitioners struggle with mathematical variance where pauses in work, such as maintenance windows or waiting for third-party approvals, artificially inflate the duration metrics. You must configure your duration business rules to account for these business hours or exclusion periods to ensure your performance reporting reflects reality rather than just idle time. Understanding how your backlog ages is equally essential for building a resilient security posture, as aging buckets provide a snapshot of stale risk. By configuring aging buckets based on the age of the vulnerable item, you can categorize your remediation backlog into discrete timeframes like 30 days, 60 days, or beyond. This categorization is vital for identifying process bottlenecks, as a high concentration of items in an aging bucket usually points to systemic failures in assignment or resource allocation rather than individual negligence. When you map these buckets onto a dashboard, you want to ensure that your view is high performance, which requires optimizing the underlying database queries that aggregate these counts. Relying on inefficient queries can lead to sluggish interface performance when dealing with large volumes of data. So consider utilizing indexed fields and pre-aggregated tables where possible. As you construct these charts, consider the audience for whom you are designing. A lead technician needs a granular table of aging items, while an executive stakeholder needs a high-level trend line demonstrating progress over time. Trendline styling and target timeline goals are the finishing touches that convert static data into a motivational tool for the remediation teams. A target timeline goal measurement effectively sets the expectation for how long a vulnerability with a specific risk score should remain in an open state. When you apply visual stressors, such as conditional coloring on a dashboard, you provide immediate feedback to the engineers and owners about which items are failing to meet the required throughput. It is helpful to visualize this using burn-down tracking matrices, which display the ideal recovery trajectory against the actual performance of the remediation activities. If your actual performance consistently falls below the target line, you can isolate if the variance is tied to specific technology stacks, geographic locations, or individual business units. By segmenting your reporting this way, you turn the dashboard from a simple compliance checker into a powerful diagnostic instrument that identifies where additional automation or staffing resources should be directed. It is through these metrics that you can effectively demonstrate the value of your security program. See you in the next lecture. Welcome back to our journey through the vulnerability response ecosystem. In this section, we will master the art of generating custom security reports to surface actionable intelligence from your vulnerability data. When we construct custom reports within ServiceNow, we are essentially building a bridge between raw security data and stakeholders who need to make informed decisions. The native reporting engine operates on the fundamental principle that any data visible in a table can be queried, aggregated, and visualized if we possess the right structural understanding. Start by focusing on dot walking, which allows you to extend your reach from a primary table, such as a vulnerable item, into related objects like the corresponding configuration item or the assigned user record. By traversing these relationships, you create comprehensive data sets that go beyond surface-level information. However, you must always be mindful of performance when dot walking across multiple layers of deep references. Even when you are strictly within the vulnerability response scope, database views become necessary when the required information exists on tables that do not share a direct, simple relationship mapping. Database views are specifically useful when you need to perform an outer or inner join between disparate system tables, such as combining vulnerability groups with actual remediation tasks. If you find your standard list queries are too slow or unable to capture the join logic you require, you should look into defining a custom database view. Once your data structure is aligned, applying advanced filter criteria requires precision, particularly when dealing with complex time-based aggregations or multi-tier status conditions. You should avoid writing filters that force the system to perform a full table scan, as this will inevitably throttle performance during periods of high platform usage. Instead, leverage index-conscious filtering by grouping common conditions logically and ensuring that your reports are not running on unindexed fields. When configuring chart formatting, remember that clarity is king. So choose visualization types that accurately represent the trend or distribution without adding unnecessary visual noise for your audience. Sharing and scheduling your reports involves balancing accessibility with the principle of least privilege, ensuring that your reports fall within the security container of the user's role. You must configure sharing profiles that specifically target groups or individual roles within the vulnerability response module rather than broadcasting data globally. For data sources, always use the secure data source restriction capabilities to prevent unauthorized users from viewing the underlying raw data that informs your summary statistics. When debugging slow report execution, begin by inspecting the transaction logs to identify if a particular join parameter or complex calculation is consuming excessive platform cycles. Most performance issues stem from redundant subqueries or incorrect aggregate processing, which you can resolve by simplifying your logic or converting complex list reports into predefined indicators. By keeping your query parameters precise, you not only improve report response times, but also enhance the reliability of the executive metrics displayed on your dashboards. See you in the next lecture. Welcome back. In this lecture, we will explore the mechanisms governing interactive security dashboards designed for distinct organizational personas within the ServiceNow environment. When we construct dashboards for a vulnerability management lifecycle, the primary challenge is not the data itself, but the context in which that data is consumed. A Chief Information Security Officer requires a high-level aggregate view of risk posture and compliance trends, whereas a remediation team lead needs granular, actionable work queues. We must leverage the responsive dashboard framework to ensure that these distinct user personas see exactly what is relevant to their specific operational responsibilities. This involves careful utilization of tabbed containers, which allow us to logically group widgets without cluttering the screen real estate or overwhelming the user with irrelevant data points. By separating high-level business intelligence from tactical remediation tasks, we successfully reduce the cognitive load on the platform users. It is an exercise in effective information architecture, where the ultimate goal is to drive informed, secure decision-making rather than merely displaying a collection of charts. The technical backbone of these interactive dashboards relies heavily on the correct implementation of interactive filters and their subsequent bindings to report widgets. When we define a dashboard, we often need to ensure that a selection in one filter, such as a business service or assignment group, propagates correctly across all reports on the page. We occasionally encounter filter propagation failures, which typically stem from the data source of the underlying report not matching the filter's target table or the associated field definitions. We must ensure that the report widgets are explicitly configured to follow interactive filters, and we should verify that the glide list or reference fields used in the filters are indexed appropriately to maintain performance. Furthermore, if we notice that a widget is ignoring a filter, we should inspect the interactive filter settings to determine if the report's data source has been excluded from the filter's scope definition. This meticulous mapping is essential for maintaining a coherent and responsive user experience throughout the vulnerability response workspace. Access control within dashboards is another area that frequently requires precise configuration to prevent information leakage or unauthorized visibility into sensitive security data. We handle this by managing individual dashboard permissions, which allow us to restrict access to specific groups or roles, ensuring that only those with the proper clearance can view high-level metric views or tactical work queues. When users report that they cannot see expected data, we should first investigate the read ACLs on the underlying tables and the specific dashboard access configuration properties. It is also important to consider that excessive widget counts or poorly optimized reports can severely degrade page render speeds, creating a frustrating experience for the end user. To improve performance, we should favor the use of aggregated data sources rather than raw table queries, and ensure that we are not performing complex joins or calculations during the initial dashboard rendering process. By streamlining these visual outputs, we ensure that the Security Operations Dashboard remains a highly efficient tool for day-to-day vulnerability management. See you in the next session. Welcome back. Today, we are diving into the technical nuances of metric definition tuning within the ServiceNow platform. When we discuss metric definitions, we are primarily concerned with the platform's ability to measure the duration of specific states or values within a record's lifecycle. At its core, the metric definition table acts as the configuration blueprint that tells the system exactly which fields to monitor and how to interpret transitions between values. If you are tracking the lifecycle of a vulnerable item, merely knowing when it was closed is usually insufficient for granular reporting. You need to understand how long that record spent in each distinct state, such as awaiting analysis or pending implementation. The system achieves this by creating instances in the metric instance table every time a tracked field changes, effectively capturing a timestamped snapshot of the state change. The architecture of these definitions relies on a script trigger parameter, which controls the conditions under which a metric is calculated. When you define a metric, you specify a table and a field, but the real power lies in the script-based approach to value extraction. If you rely on standard field-to-field tracking, you gain basic duration data, but high-velocity transactional tables, such as those housing high volumes of vulnerable items, often require custom logic to prevent performance degradation. You must carefully consider the overhead of the business rules that execute these triggers to ensure they do not become a bottleneck during bulk updates or automated imports. Proper tuning involves ensuring these triggers only fire when a meaningful transition occurs, avoiding the creation of redundant or empty metric instances that clutter your database and inflate your reporting latency. Value extraction routines allow you to derive custom metrics, such as calculating the time an item remained unassigned or the total duration it spent in an exception state. By utilizing the value field within the metric instance, you can store granular data about ownership changes, which is vital for calculating mean time to respond metrics. Implementing a script that handles these transitions requires a solid grasp of glide record interactions and the underlying logic of the duration calculator. You should always aim to write lean, efficient scripts that avoid heavy queries within your metric definitions, especially when processing records that are frequently updated by automated remediation flows. If you find your system generating duplicate instances, it is often a sign that your trigger conditions are too broad or that conflicting business rules are firing on the same field updates during record operations. Management of exception durations is a common requirement in vulnerability response, where you need to track how long a vulnerability remains deferred or accepted from standard remediation targets. By creating a custom metric definition specifically for the exception request state, you maintain a clean audit trail that supports compliance requirements. This involves setting up the definition to monitor the state field and using a script that specifically looks for changes into and out of the exception status. During this process, be mindful of how reassignment counts are logged, as these metrics often serve as proxies for complexity or process friction. Maintaining clean data in these tables ensures that your performance analytics dashboards provide an accurate representation of operational health rather than distorted duration figures caused by noisy data. Finally, performance tuning on high-velocity tables is often a matter of minimizing the compute cost per transaction. If you notice that your metric instance table size is exploding, despite having relatively low record counts, it is likely that your definitions are capturing state changes that have no analytical value. Regularly auditing your metric definitions against your actual reporting needs is a best practice for maintaining a performant ServiceNow instance. Focus on refining the conditions and scripts to be as restrictive as possible, ensuring they only capture the state transitions that truly impact your ability to evaluate security operations. By following these principles, you ensure that your metrics remain a source of insight rather than a hidden performance tax on your platform infrastructure. See you in the next lecture. Welcome back. In this session, we will examine the technical intricacies of optimizing analytical data structures within the context of your vulnerability response implementation. When we discuss the performance of analytical structures in ServiceNow, we are essentially talking about the efficiency of data retrieval against the platform's underlying database. Vulnerability response environments often accumulate massive volumes of vulnerable items and detection data, which can quickly turn simple dashboard queries into expensive operations. The primary goal here is to ensure that your reporting layers do not conflict with transactional performance. When a query hangs or a dashboard fails to load, it is usually because the engine is forced to perform a full table scan instead of utilizing a targeted index. By understanding how the platform stores and retrieves aggregate data, you gain the ability to preemptively address these bottlenecks before they reach your end users. We need to look at how database views function, particularly when they involve complex joins across multiple tables. If you are joining the vulnerable item table with assets and scanner results, that query needs a clear path through the index tree, or the system response time will degrade linearly with the size of your data. Performance tuning starts with the realization that not all data needs to be live or fully indexed at all times. Service-level agreement breaches and security posture metrics rely on aggregates, which are periodically computed to avoid recalculating thousands of records on every dashboard refresh. You should be familiar with the concept of aggregate data table caching, which decouples the high-performance report visualization from the volatile transactional data. If you notice that your vulnerability response dashboards are consistently slow, the first step is often to identify long-running reporting queries through the slow query logs. Once you isolate the culprit, you can determine if a database index is missing or if the view itself is structurally inefficient. A common mistake is building views that dynamically traverse complex relationships. Instead, you might consider flattening specific fields or utilizing specialized reporting index structures to handle the heavy lifting. This allows the reporting engine to fetch pre-calculated values rather than attempting to compute them on the fly. Designing for performance also requires a disciplined approach to data lifecycle management and archival strategies. As your vulnerability repository grows, maintaining historical data in the active tables inevitably slows down your reporting metrics. You must establish clear data pruning rules to move stale or resolved findings into archival storage, which physically removes them from the active reporting scope. Excluding resolved items from your daily operational views isn't just a best practice for clarity. It is a critical performance measure that keeps your primary tables lean. When you refrain from scanning records that no longer require action, you effectively reduce the database load and ensure that critical reports render within established timeframes. Furthermore, pay close attention to how your automated grouping patterns interact with your analytics. If you have overly aggressive grouping logic that triggers frequent updates or recalculations, that overhead will manifest as performance degradation in your reporting modules. Balance the need for granular data visibility with the reality of database execution constraints to maintain a responsive environment. Beyond table pruning and indexing, you should analyze the behavior of your data collection jobs. These workers are responsible for populating the performance analytics indicators that drive your executive dashboards. If these jobs are configured to run during peak hours, they can lock resources needed for transactional record updates, leading to platform latency. Proper configuration involves staggering these collection intervals and ensuring that the queries feeding these metrics are highly optimized. We often suggest reviewing the database index usage profile specifically to see if the columns used in your report filters are indexed. If you find that a primary filter on a dashboard consistently results in a full table scan, that is a direct candidate for a new custom index. Just remember that while adding indexes improves RED performance, it carries a slight cost for write operations. Therefore, treat your indexing strategy as a focused intervention. By reconciling these variables, you ensure that your security operations team is always looking at high-fidelity data that does not come at the expense of system health. See you in the next lecture. Welcome back. In this final session, we will synthesize the foundational concepts and technical patterns established throughout this curriculum to finalize your readiness for the certification exam. Our journey began by dissecting the core architecture of the vulnerability response application, focusing on the essential plugin installation processes and the granular access control requirements that secure the platform. We transitioned through the scanner integration layer, where we examined how third-party vulnerability data is ingested, normalized from sources like the National Vulnerability Database, and reconciled against the CMDB to manage unallocated assets. Understanding the reconciliation log diagnostics is not merely an academic exercise. It is the practical heartbeat of ensuring that vulnerability data maps correctly to existing configuration items. We discussed how CMDB linking serves as the bedrock for all subsequent risk prioritization, ensuring that when you calculate risk, you do so against accurate, enriched asset data rather than orphaned hardware or software records. If the asset enrichment is flawed, the risk scoring, which we explored via vulnerability risk calculators and business-specific impact assessments, will fundamentally fail to provide the context needed for effective remediation. Moving into the realm of remediation, we focused on the structural grouping patterns that organize thousands of individual vulnerable items into manageable, actionable remediation tasks. The architecture of vulnerability groups allows for automated assignment, ensuring that the right security or infrastructure teams receive relevant issues based on predefined criteria. We covered the nuances of exception management workflows, which are critical for maintaining compliance when immediate patching is not an operational reality. Furthermore, we investigated how to orchestrate automated flows using Flow Designer and its tight integration with ITSM interfaces to bridge the gap between identification and resolution. Effective automation here requires a clear understanding of the reassessment loop, ensuring that once a patch is applied, the scanner integration recognizes the change and subsequently closes the loop within the ServiceNow instance. The final pillar of our discussion centered on the performance analytics framework and the generation of actionable metrics. Generating reports is trivial, but tracking remediation velocity and aligning dashboard security with operational needs requires a calculated approach to metric definition tuning. We examined how to optimize analytics data to ensure that stakeholders receive timely visibility into the risk posture of the organization. As you approach the examination, remember that the questions will often test your ability to diagnose failure modes within these pipelines. When a scanner fails to ingest data, or when a vulnerability group does not trigger the expected assignment rule, you must be able to trace the issue back through the integration architecture or the underlying application properties. Establishing proper testing habits involves mocking these scenarios in your head, asking whether a logic flow behaves as expected when integration variables are constrained or when CMDB data quality is suboptimal. As you prepare to sit for the exam, ensure you have a firm grasp on the distinction between transient configuration issues and systemic architectural limitations. Focus your review on the application properties and the specific logic paths that dictate how vulnerability risk is propagated through the system. Pay attention to how the system handles duplicates and how data is filtered during the ingestion phase, as these are frequent areas for technical nuance in certification questions. Your ability to distinguish between remediation tasks and vulnerability groups will be essential, as these entities serve different roles in the lifecycle of a vulnerability. Maintain a diagnostic mindset, looking for the root cause of issues in the logs or the reconciliation history rather than merely focusing on the end-user interface. This systematic review should provide the confidence needed to translate theoretical knowledge into correct examination outcomes. Good luck with your exam preparations.